Hi there, what's up? And welcome to the stream. So before the stream even begins, there already a question in chat, which is awesome. It says, please, do you recommend studying from this book as a first course in complex analysis, since I never studied it before? Which is an excellent question, and I think it deserves a good answer. So I think So perhaps let's say it really depends on your objective. I mean, this is not my first exposure to complex analysis. I used the textbook by Brown and Churchill, which is a great book. Don't get me wrong. And a lot of complex analysis textbooks are very similar, compared to, say, subjects like differential equations and more functional analysis. Complex analysis textbooks are quite similar. So why do we decide to take a look at the Russian version? This is the Russian textbook. So let me just give you, this is the book we're going to go over. Actually the main one, not the only one. Hi, private. What do you mean private? Hi Leo, welcome to the stream. So chat, this one, this book, it has its advantage and perhaps disadvantage. Disadvantage in the sense that it is cultural, right? Not mathematical. Hi, why do I, so to put long story short, okay, I would still probably recommend a single textbook in a Western tradition, okay? Simply because in the Russian tradition, typically you have a textbook and a separate problem book. So you need two things. So the way "Привет" is hello in Russian. Okay, "Привет." Hello, the new series. I mean, this is not a new series because, well, complex analysis was something that is promised on the channel a long time ago. And I figured doing these live just helped me prepare with the videos, so might as well just do it live. And yeah, "Привет" is hello in Russian. That's right. So I was saying, like this book, like many Russian books, it's mostly theory and examples, but not many exercises. So the Russians tend to have the textbook and problem book separate. Okay, there are many famous examples of this. So if you try to learn the theory from the first time, it might be just convenient for you to have one source. So that's why if you're learning the theory from as a so to say from a course, or learning the first time as a self-learner, I would still recommend the book by Brown and Churchill. It's called Complex Variables and Application. It's now in its 9th edition. It's a very solid one, and it's very approachable. And it's got problems at the back of the section, so it's easier for you to locate the appropriate exercises for each section. However, if you like complex analysis, I strongly recommend you check out this one by Markushevich, The Theory of Analytic Function, a Brief Course. So first of all, who is Markushevich? Markushevich was a Soviet mathematician, mathematical educator. I'll look at the chat in a bit, okay? So this is the Wikipedia page for Markushevich. So Markushevich was a Soviet functions theorist. So he worked in mostly complex variables and, I believe, functional analysis. So this theory named after him is one in complex analysis. Okay, and his text on complex variable is the standard in the former Soviet Union, in Eastern Europe, and was highly influential. So this one, the book that we're using today, is called A Brief Course. However, if you just take a look at the the content list, but you can see it's not quite brief at all, right? So, I mean, if you see the term brief, you might expect it's going to be a short one. But no, it's still over 400 pages. And some of the topics are quite advanced. So we'll go over the content list in a bit. So why is it called brief? Because Markushevich has a more extended treatise on complex analysis. And that one is called Theory of a Complex Variable, Theory of Functions of a Complex Variable. And this one has 3 volumes in total, and it has well over 1,000 pages. So in comparison, this one is brief. Okay, so this one is extremely thorough. I actually have a physical copy of it. Okay, and I actually have the Russian version, right, of the first volume. A friend of mine, a Russian friend of mine, brought a copy from Georgia, the former Soviet Republic of Georgia, which is awesome. So, and I think it would be a great comparative reading exercise for me to read the English version on one end and the Russian version on the other, to practice my Russian reading. So this one, as I said, Markushevich was, and still, I mean, his text is still the standard of complex variables in Russia, in the former Soviet region, etc. And by the way, the book I mentioned earlier, the book by Brown and Churchill, perhaps a more Western introduction, more standard Western introduction to the subject, cited this book repeatedly, especially when it comes to more complicated proofs. So this book is known for its just extreme thoroughness. Okay, and this one is the main one. Okay, it's the main one that we're going to do. However, there's another one that's worth mentioning, and also of Russian origin, Soviet origin. This one is called The Theory of a Function of a Complex Variable, written by A. Sveshnikov and A. Tikhonov. So this one is more applied. This one is more applied. A. Sveshnikov was a Soviet mathematical physicist. This guy. He looks like this. That's him. Lived for passed away at 98 years old. Okay. Alexei Sveshnikov was a mathematical physicist, and Tikhonov, Andrei Tikhonov. Andrei Tikhonov, he was just extremely productive. He in topology, he has results in topology, functional analysis, mathematical physics, and ill-posed problem. And in particular, in the applied community, he is particularly known for the founder of modern inverse theory. So as you can see, in typical Russian fashion, there's very little separation between quote-unquote pure versus applied mathematics. So Andrei Tikhonov, among others, were heavily involved with the Soviet nuclear and space program, and he was the founder of the computational mathematics and cybernetics department at Moscow State University. Just extremely influential individual, both in the USSR and worldwide. Okay, so as I was saying, this one is more applied. It's got more application with more application of complex variables in mathematical physics. So, for example, this I believe is some kind of capacitor, okay, on the cover. Anyway, that's why we're going to bounce around kind of between Markushevich and Sveshnikov and Tikhonov. Okay, but today we're going to just focus on Markushevich. All right, so let me just, by the way, as I was saying, these two books, in typical Russian tradition, don't have many exercises. So this is just how Russian does things. That's their format, preferred format. So if you want to have a taste of Russian style problem set, this is the one. a collection of problems on complex analysis. So this one actually pairs with the Markushevich text pretty well. It's published by Dover, so it's very affordable. It's got over 1,500 problems, and the problems are the difficulty varies a lot. Okay, there are some simple ones and there's some highly non-trivial ones, and the range of coverage is also very wide, including some of the things that are rarely taught in basic complex analysis nowadays, things like elliptic functions, which is extremely powerful. I wouldn't call it extremely powerful, but the theory of elliptic functions was the pinnacle of mathematical achievement throughout the 19th century. It attracted attention of generations of just top-tier mathematicians. So this one covers that. Anyway, let me catch up with chat. All right, so wow, there's a lot of messages here. Armin, hello. Farah, hello. What is your background, like degree and stuff like that? I always get these kind of questions. My background is in statistics and applied mathematics. My highest degree is master's degree in applied mathematics. I'm not in academia. Leo, thank you so much for joining the stream, for just stopping by and say hi. Good. All right. Leo even wrote Chinese in the chat. That's awesome. That's awesome. Qwerty says, my father had many books from mere publishers. It was affordable, was one of the main reasons. Don't know they still exist. Unfortunately, they don't. Mostly science and math related. Some folk stories typing too. Exactly. I mean, this is, in my opinion, the best legacy. Science, mathematics, that sort of stuff was the best legacy of the USSR. So anyway, 再见呢? Okay, sure. Introduction to measures. Actually, I don't know that one. I know there's a Russian text on measure theory written by Shilov. Shilov, Shilov, by Shilov. That was a good one. So brief introduction handbooks are the most fearsome. Haha, I know, right? The Russian school is still producing notable figures as mentioned here. I don't know, actually. I don't know. But so, of course, the lineage is still there. The lineage is still, I don't know, like any particular contemporary figure. Perhaps one guy is worth mentioning. Because I actually read some of his work. Evgeny Derdishnikov. He is a student of Sveshnikov, so he has the lineage of Tikhonov and Sveshnikov, and he worked in numerical mathematics. And in particular, I strongly recommend his text on a numerical linear algebra. It's called once again a brief. This one's actually brief. Brief introduction to numerical analysis, barely 200 pages, and is very deep. By Derdishnikov, he is still in Russia. He still works in the Moscow State University. A lot of Russian and Soviet mathematicians emigrated to the West near the fall of the Soviet Union and during the 90s, during the economic horrors of 90s in Russia. But still, the lineage, the Soviet tradition is still there, very much alive, and they just unfortunately, I don't think it's unfair to say that countries like Russia, and Ukraine, and Belarus, those places suffer from brain drain. They have top-tier, just foundational education, but they can't keep their top graduates, if that makes sense. All right, enough about politics and all that. Pyramid dropped this to grow mushroom. Hello from Spain. Thanks for all the series we've been putting out lately. No, my pleasure. Seems like Vladimir Arnold was one of the last notable figures I've heard of. Arnold was, well, a student of Kolmogorov. Arnold was a student, and he was he worked in diverse area. Perhaps that's why he's more well known. Okay, and he was also personality-wise an interesting person. He liked to sometimes he has controversial opinions, which perhaps also caught a little bit of a headline. He liked to, in particular, pick fights with the Bourbakis. Arnold, especially, like, yeah, he wrote some rather, just say, funny stuff about the French schools. So Arnold, yeah, definitely worth checking out. His text on mathematical methods in classical mechanics was a classic. It's still very much highly revered. I mean, if you don't want, if I make a question for you, streaming Russian for mathematicians who remember don't want to study some physics with Chinese references. Actually, I don't know because I didn't study, my advanced degree in China, and to be honest, it's kind of difficult for me to read Chinese mathematical or just scientific literature because I have to do this manual translation. It's like a concept in physics, math, stats. Oh, I have to look up, oh, what's the Chinese term, and that sort of thing. It's not convenient for me. And of course, I'll do my best. If you want, let's say, original Chinese contribution to a particular subject that is originally not written in Chinese but then translated, I'll take a look. But definitely, so one thing on top of my head is Chung. So if you guys interested in the probability theory, you guys probably are. Probability theory, stochastic calculus, that sort of stuff. Chung's probability at both elementary and graduate level are extremely good. Chung's probability. So they were written in English, so there's no need to learn Chinese to read Chung's book. Okay. So actually, most of top-tier mathematicians from China write in English to maximize international impact. I mean, at least they do so. They write in Chinese and English in parallel. Right? So actually, that was sort of the situation in the early Soviet period. So during the early Soviet period, I mentioned this in my Russian for Mathematicians stream. During the early Soviet period, top-tier mathematicians like Kolmogorov, they didn't just write everything in Russian. So that was something that only happened later. So before, well, the Soviet Union was not a scientific powerhouse during the Cold War era. So after the establishment of the Soviet Union, the Russian state was still very much agrarian, and there was a lot of illiteracy in the country, even though there are concentrated areas that are more advanced. Overall, the country was backward compared to Western Europe, like Germany and France. So a lot of Soviet and Russian mathematicians were publishing in those languages, in German and in French, to maximize international impact, because like during the interwar period between the First and the Second World War, Germany and France represented the top, so to say, top level of mathematical research as far as the pure math department is concerned. So actually, Kolmogorov wrote his treatise on probability theory. This one, Foundation of the Theory of Probability, originally in German. So this wasn't written in Russian or English for that matter. It was written in German. Because Kolmogorov wrote this in response to one of the Hilbert's problem. The axiomatic foundation of modern probability theory. Kolmogorov wrote that in German. And unfortunately, there was this unfortunate event during the 1930s, during the Great Purge, so called the Luzin Affair. So what's the Luzin Affair about? Basically, Nikolai Luzin was one of the founders of the modern Russian Soviet school, especially strong in real analysis, measure theory, topology, that kind of area. And Kolmogorov, among others, were his students. So, yeah, Nikolai Luzin, actually in our measure theory series, and very soon we will see a theorem called Luzin's theorem. It's in Axler's book. And actually, let me just show that real quick. It's in Axler's book. And also Luzin's PhD advisor, Yegorov. So, yeah. These are nowadays standard results in measure theory. So we go to chapter 2. We're currently in chapter 2 right now. So convergence of measurable function here. It has to do with, it's called the Yegorov theorem. Yegorov was Luzin's PhD advisor, Dmitry Yegorov. He died in 1931. Guess what happened? And the second theorem is Luzin's theorem. Okay. After Yegorov's theorem, we have the Luzin theorem, Nikolai Luzin. So this one, it also has to do with the properties of measurable function. So they were producing world-class mathematical results. However, during the Great Purge, Yegorov was accused of being a counter-revolutionary against the Soviet state, because Yegorov, Luzin's advisor, where is Yegorov here? Dmitry Yegorov. He was very religious. So his, although he wasn't a dissident, a political dissident, his religious conviction made him an easy target. So he died in a hunger strike in 1931. Yegorov, he was arrested and imprisoned as a religious sectarian, and soon after was expelled from the Moscow Mathematical Society. Upon imprisonment, Yegorov began a hunger strike until he was taken to the prison hospital, eventually to the house of fellow mathematician, I don't know this person, where he died. So very tragic, very tragic. So Yegorov died in 1931, and the infamous Luzin affair happened in 1936. So at the time when Yegorov's tragedy happened, I believe Luzin was abroad. So Luzin came back to the Soviet Union, and not long later he was accused by among all people, his former students, that there appeared to be counter-revolutionaries among mathematicians, and including a person we've seen on the channel, Lev Pontryagin. So we've seen this name, Lev Pontryagin, in our stream on optimal control. Right. Pontryagin is also very productive in differential topology and optimal control. However, he was also infamous for being involved in very questionable political activities. Okay, let's just put it this way. So one of the actual recurring themes on this channel is do not worship scientists. We honor their labor, but we do not regard them as saint or anything. Scientists certainly aren't. They are just as fallible as other fellow human beings. So I don't know what his motivation was, but he decided to accuse his teacher, Luzin, of being a counter-revolutionary. So this became an infamous event against Luzin, and just in the Soviet mathematical community as a whole. And one of the accusations against Luzin was the fact that, quote unquote, was the accusation that he only published second-rated papers in Soviet journals, or in Russian, in Soviet journal, while reserving his top-tier results in foreign languages. So he only published the attackers of him. I don't know if it was accused by Pontryagin, but one of the accusations against Luzin was that he only publishes second-rated papers in Soviet journals and keeping his best results to foreigners. So eventually, it was such an infamous event because lots of great names in the Soviet mathematical community, Alexandrov, topologist, this one actually I don't, this person actually I don't know, but Hinshin, probability theorist, Kolmogorov, needs no introduction, also contributed to our great disappointment. Okay, our beloved Kolmogorov also contributed to this just unnecessary event. Okay, but then again, you might argue those people are also under pressure by Stalin's secret police to, because if you, let's say, because the wind was was already blowing against Luzin, say under that kind of political pressure, these, well, just great mathematicians, they folded under political pressure. But what ended up happening is, unlike Yegorov, who unfortunately, who tragically died, Luzin was only mildly punished. So Luzin lost his academic post. So here, as you see, although the commission convicted Luzin, he was neither expelled from the academy or arrested. But his department in the Siklov Institute was closed, and he lost all his official positions. So he was academically ruined, but at least he lived. Okay, which was already a great outcome compared to a lot of the victims during the Great Purge. So he wasn't sent to Gulag or anything. So he was finally rehabilitated in 2012, long after the Soviet Union was no more. So what happened later is that the Soviet mathematical community did not suffer too much when it comes to its productivity. Okay, the research was still pumping out, mathematicians were still being trained, and the Soviet Union became a mathematical powerhouse, the world-class mathematical powerhouse. There's no denying of that. However, pretty much all of the contributions, all of the papers, the books were written in Russian. So the Soviet mathematicians stopped publishing in foreign languages anymore. I guess it has a lot to do with the Luzin affair, because due to one of the accusation against him was that he supposedly only publishes second-rated papers in Russian and best ones in foreign languages. So there is that. Anyway, so that causes the unfortunate self-imposed isolation by the Soviet community. So anyway, that was a bit of a side tangent, which I think is interesting because mathematicians in particular, mathematicians don't exist in vacuum. They exist in a society, and they were forged by the society, and their work was influenced by it. Okay? Because of the self-imposed isolation, among other things, the Soviet mathematical community have to cope with that reality. So as a result, as a positive result actually, there's very little artificial separation between pure and applied mathematics. So because the country is isolated, mathematicians in all areas have to collaborate among themselves. So this created this unique culture of cross-disciplinary collaboration among practitioners. Unlike, this is a little bit different. I mean, of course, specialization do exist. However, it appears that there is this great emphasis on the unity of the mathematical subject compared to what we see in the West. Right? A characteristic of Western academia is hyper-specialization. Like even for a student at a very early stage, like if you let's say, if you're applied math major, and in your first year, chances are you will be learning calculus from James Stewart and linear algebra from Gilbert Strange-based text. And if you're a pure math major, chances are you'll be studying calculus from something like Spivak, right, and linear algebra from Axler. And the schism continues. It starts from the very first year, and the schism continues. In the third year, as an applied math major, you probably do partial differential equations, numerical methods, that kind of stuff. Whereas pure math major studies real analysis, abstract algebra, that kind of thing. So even to this day, I mean, I've still heard like sayings online, read on Reddit or something like that, says, oh, abstract algebra is pure math. And partial differential equations, PDE, is applied math. It's such an artificial the barrier, man, because scientifically there's no such barrier. There's no such barrier. Like, I would just give one example. Right? Fourier series started out as an applied tool to study wave motion, heat transfer, that sort of thing. But its properties are so wild and counterexamples so pathological that mathematicians had to look at the very foundation of mathematics itself. Questions such as what it means, what does the word function mean? Right? What do real numbers mean? A question like this, their importance of them, the importance of which were only realized after a thorough investigation of Fourier series. So Fourier series was one of the great impetus in the study of real analysis and measure theory, which are nowadays quote-unquote considered as pure math, apparently. So you see, the arbitrary distinction between quote-unquote pure and applied mathematics, in my opinion, is hurting mathematics. So one of the meta goals of this channel is to promote cross-disciplinary communication. Like, so we don't, we're not going to stay, okay, because, I mean, this channel is mostly applied math. It's mostly applied math. We always have certain concrete goals in our mind, and we really do theory crafting on its own sake. But at the same time, we aim to make different groups of practitioners understand each other's language. Right? So that's why we're that's why it feels like, okay, we're doing too many things, right? Okay, so perhaps there's going to be a little bit of adjustment for that, but that's the overall philosophy for the channel. All right, enough digression and history, so let's actually get on with the math. Okay, so anyway, let me close this, just close everything, and I will do the actual content, the actual math. So the actual math start here. Anyway, I will still, for the most part, I will do the writing in my notepad because I don't want to get into copyright issue, even though mere publisher is no more. I still want to do most of the writing, unless say an author or a publisher like Axler explicitly stated that their work is open source. Okay, so but I mean, as an open secret, you can find the scanned PDF version on Internet Archive. Okay, just search Markushevich complex analysis, and the first result will be available. It's not that hard these days to find free books. All right, so okay, so let's start with the main motivation. The topic, sorry, the book, the name of the book, okay, is called the theory of analytic functions. of a complex variable. So first of all, we have to understand a question, or understand okay what it means to what it means for a function to be analytic. Okay, so before we dive into the world of complex numbers, let's first take a look at the definition of analytic functions for a real variable. So let's say f of x is a function of a real variable, and x is greater than a, less than b. So it's defined on an open interval on the real line. A to b can be infinite. Okay, so a is greater or equal to minus infinity, less than b is less than or equal to infinity. So the interval can be infinite. The function is analytic in this interval if in the neighborhood of each point inside the interval, it can be represented as a power series. So basically that's the idea. Analytic functions have power series expansion. So put it formally, we say f of x is analytic on a to b if for every point x naught in the interval a to b, f of x can be written as a power series. F of x equals a naught plus a1 x minus x naught plus a2 x minus x naught squared, blah blah blah. Okay, so the pattern continues. So this is such a natural thing if you think about it, right? Such a natural criteria because the function we are familiar with, arguably familiar with the most in elementary mathematics is polynomial. So analytic functions really just a generalization of polynomial because power series can be seen as polynomials of infinite degrees. Okay, so the general term would be an x minus x naught squared, not square, n to the n plus, and so on. Okay. So this statement actually says a few things simultaneously. This equation, first of all, it says this is true. Okay, for every x naught in this interval AB, on a neighborhood. Okay, the series doesn't need to be true for all x in AB. Okay, for all x in B, on some neighborhood. I'll draw a picture real quick. Some neighborhood of x naught, we have this relation. So this is the real line. This is the interval a to b, open. Okay, open interval a to b. That's important. And x naught is an arbitrary point in the interval. If on some neighborhood of x naught, some neighborhood, it just means an open interval centered at x naught. Okay, neighborhood, the name neighborhood means x naught plus or minus epsilon, also open set. It just means that in some points that's near x naught, you have this expansion. And by that we mean, first of all, the series on the right-hand side converges. The series on the right-hand side converges. Remember the definition of an infinite series. Remember the definition of convergence of an infinite series. It means that the partial sum has a limit. Right, so here, this is the infinite sum. In general, infinite sum has no meaning. In general, infinite sum is a meaningless expression. However, you can assign a meaning as follows. Say, if you just sum up the first n terms, which is a finite sum, that's a well-defined notion, you get a sequence with index n. As n tends to infinity, if the sequence has a limit, we call that limit the sum of the infinite series. All right? So here, this statement, this equation, what is saying is that the right-hand side is a convergent infinite series, and its sum, the limit of the partial, aka the limit of the partial sum, equals f of x. Okay, so there are two things happening simultaneously, because simply having the right-hand side being convergent still may not guarantee it equals f of x. Okay, so there are actually multiple things happening in this statement. All right, so that's the definition of an analytic function on a real line. Okay, of course, we've seen such functions a lot in regular calculus. Examples: you got polynomials. This is the most obvious example because that's just a finite. It's just a finite sum, right? So polynomials always can be written in this form as a naught plus a1 x minus x naught blah blah blah, and the highest power is the degree. So polynomials are obviously analytic functions, and also well-known functions like exponential, sines and cosine. And actually, let me write down the series expansion for e to the x and whatnot. All right, so if, let's say, we're just going to use the classic expansion, okay? E to the x, just going to expand x naught at x naught equals 0. Okay, when x naught equals 0, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on equals the sum of x to the n over n factorial, where n goes from 0 to infinity. Right, so exponential function, it can also be written as a power series. E to the x is also analytic. In fact, analytic everywhere on the real line. I mean, I just did an example of expansion at the base point x naught equals 0, because that's the most well-known formula. But it is possible to expand e to the x around or about any base point on the real line. All right, so a few more well-known examples from calculus. Sine of x is x minus x cubed. So the series for sine of x when expanded at x naught equals 0 only has odd powers. So x to the 3 over 3 factorial plus x to the 5 over 5 factorial plus x to the 7th over 7 factorial. And the pattern, I messed up the sign here. Should be the sign should alternate in the series for sine, okay? Plus and so on. This equals the sum of n from 0 to infinity, x to the 2m plus 1 over 2m plus 1 factorial times minus 1 to the n. Okay, and cosine of x, because we will be seeing these series again in complex variables. And symbolically, just a spoiler alert, symbolically they will look exactly the same. So in complex variable, you literally, as we will see, you just replace x by z, a complex number. Here we're still dealing with real numbers, okay? And by the way, as far as speaking of real numbers, so this raises the question of how much real analysis you need for complex analysis. And the answer is not a whole lot. The answer is not a whole lot. And when it comes to not a whole lot, but still important. So when we use some of the foundational results in real analysis, we'll just simply state so without actually proving it. And we'll mostly be dealing the aspect of complex analysis that's independent of real analysis. Okay, perhaps independent is not appropriate because, as I mentioned, there are some foundational results that relies on real analysis. We're just going to treat the results in real analysis as black boxes. That's what I mean. Okay. So, for example, you do need notions like things like compactness and the real number is complete, that sort of stuff. But we're just going to use those results, assuming that the real numbers is understood, and just investigate what's happening on the complex plane. And actually, that's what's historically what happened. Another historical digression. Complex analysis was matured before real analysis. So this might sound a little bit surprising because to a layman, complex numbers are harder. Complex numbers sound made up. You got this weird looking square root of -1 there. Whereas real numbers feels completely trivial. It's just point on a line. What else can be said? But for a mathematician, the situation is completely opposite. The jump from rational numbers to real numbers was humongous. The work that is needed to go from rational to real is very deep. However, if you assume that the real numbers are understood, going from real to complex is very, very, very smooth. Now, not a whole lot of work needs to be done to go from real to complex. So the foundational questions about the nature of real numbers was only resolved in the second half of the 19th century, whereas fundamental results in complex analysis, like as we'll see later on in the series, Cauchy's integral formulas, and including power series, that sort of stuff, was already well known in the early part of the 19th century. So Cauchy did a lot of heavy lifting when it comes to developing complex variable theory. His work on real variables were sometimes questionable. Yeah, for example, Cauchy did not distinguish the notion between uniform continuity and continuity, which made him, resulted in a few mistakes in his papers. However, was his work on complex analysis largely still stand up to today's standard. Okay, so perhaps an interesting fact here. Complex analysis was matured way before real analysis. Okay, so these are examples of analytic functions on the real line, and in fact they are analytic on the entire real line. Okay, not just on some subsets of real line, on the entire R, on the entirety of R. So minus infinity to infinity. There you go. Okay, so these are well-known functions from calculus, and also there are rational functions. Rational functions are ratios of polynomial. Rational functions. Rational functions in general aren't analytic on the entire real line. Okay. Rational functions, and you have the other trig function like tangent, cotangent, secant. So these functions are also analytic on subsets of the real line. Cosecant. Are analytic in intervals that do not contain points at which the corresponding function is not well defined. Or analytic at points where functions, should I say, I mean, we haven't even never actually defined the notion of analytic at a point, right? We only discuss analytic on the intervals, right? How do I phrase this? So it should be analytic on intervals that do not contain points where the function is undefined, okay? So just say analytic on their domain. That'll be cool. On intervals. Actually, we only define analytic on intervals, but their domains aren't always intervals. So let me just say on intervals where the functions are well defined. Okay, that's a good description. I'm happy with that. Well defined. Okay. So i.e. not infinite, because rational functions tangent is the ratio between sine and cosine. You always have this issue of potentially dividing by 0. Rational functions is a ratio between polynomials, p of x over q of x, right? So you got issues with dividing by 0 there. Cotangent is 1 over tangent. Secant is 1 over cosine. Cosecant is 1 over sine. So they all have points at which the function blows up to infinity. So as long as the intervals do not contain these points, the functions are analytic. You can write down their Taylor series basically Taylor series or power series expansion, although the coefficients aren't always easy to obtain. So for example, if you want to get the expansion of the tangent, you want to get the expansion for tangent at x equals 0, well, what do? Well, you can do a long division of the sine series and cosine series, just like how you divide polynomials. Actually, we'll do that. And the general expression can only be specified using the so-called Bernoulli numbers. Okay, so as an exercise, you know what? Let's do the power series expansion of tangent as an extra example. It's not in the book, but I felt like we might as well see an example of such operation. So because it's not in the book, I'm going to use a green color. So the first few terms in the power series expansion of tangent x for at x naught equals 0. So to do that, we simply use the fact that tangent x is defined as sine of x over cosine of x. All right, and we're going to use a series for sine of x and cosine of x, so which is x. I'm going to actually factor out the x in the sine of x. So we got x times 1 minus x squared over 3 factorial minus, actually plus, okay, x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus and so on. All right, and divide that by the cosine of x, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus and so on. So let's divide these two series as if they are polynomials by using the long division. So let's do that. So here I'm just going to set up the long division equation. Okay, so there you go. This is the numerator and this is the denominator. Just like how you do division of polynomial in high school. Like that. All right. So the first coefficient is 1. So let's put a 1 on top. Anyway, so 1 on top, and you get this, just the whole thing down here, and you do the difference. there might be some arithmetic needs to be done. So what's minus 1 over 3 factorial plus 1 over 2 factorial? Okay, do that. This is minus 1/6 plus 1/2. This is 1/3. This is 1/3. Okay. So here you got positive x squared over 3. All right, and we do x squared. Actually, hang on a second. This is x to the 4th. Yeah, that would be weird if the powers don't match. Okay. Anyway, so let's keep doing the differences. Well, now you need 1 over 5 factorial minus 1 over 4 factorial. Okay, so I guess you can take out 4 factorial, 1 over 4 factorial, and this will be 1/5 minus 1, which is 1 over 4 factorial times minus 4 over 5, which gives you minus 1 over 5 times 3 factorial, and that's minus 1 over 30. All right, so yeah, there we go. You say you have this is a minus 1 over 30, so x to the 4th over 30. And here you have the third difference, which is minus 1 over 7 factorial plus 1 over 6 factorial. Take out the 1 over 6 factorial, you got minus 1 over 7 plus 1. So that's a minus 6 over 6 factorial times 7. All right, so that's a minus 1 over 5 factorial times 7. Okay, so the numbers are getting crazier. Okay, so we still need to, maybe we'll just leave it here. Okay, maybe we'll just leave it here. So if you want, if we actually need the simplified version of this, we'll do so later. So here you just put minus or plus, actually. I think I made a sign mistake. It should be plus. Yeah, 1 minus 1/7 is a plus sign. What am I doing? Okay, so there's a plus sign. You got to be very careful doing this sort of manual calculation. So anyway, here we have that division thing going, and now because of the leading term, actually the leading term would be the lowest power because there's no highest power here. This is a little bit different when you do polynomial division, right? In polynomial division, you typically write the highest power at the beginning and move down from left to right, that sort of thing. But here, because of, well, power series don't have a highest power, we just have to do things this way. And then you put up a, what's that? Well, just x squared over 3. So multiply this thing by x squared over 3, you got x squared over 3 minus x to the 4th over 3 times 2 factorial. All right, and you got plus sign x to the 6th over 4 factorial times 3. Okay, and you keep doing the difference. Okay, so yeah, I mean, this process can obviously be repeated, so I'm just going to skip the details. Okay, so here, if you just want the first few terms, I mean, I just got the first 2 terms, right, as you can tell. So this will be x times 1 plus x squared over 3 plus dot dot dot, and this will be x plus x to the 3 x cubed over 3 plus, and so on. The general coefficient in tangent would require the usage of Bernoulli numbers. So let me just put a remark here. This is long division. which is good for the first few terms. However, if you need the general coefficient, general formula for the expansion coefficient, calls for the use of what we call the Bernoulli numbers. And it's quite complicated. Yeah, tangent is an exponential generating function, exactly. Exactly, so that's actually how Bernoulli function can be defined. One of the ways to define it is to use generating functions. Exactly, Leo is completely right. And it's used in combinatorics. Bernoulli numbers are hugely important in combinatorics. And actually, combinatorics is one of the area, perhaps surprisingly, that complex analysis is greatly useful because of the generating function technique. Okay, so let's say you want to calculate the sequence, and the sequence itself is rather difficult to analyze, so you convert that to a generating function. And this is such a powerful technique that is used throughout all kinds of areas of mathematics. Fourier transform, Laplace transform, and also probability theory got the moment generating function, which are essentially just the same thing. They're generating functions that that contains exactly the same information as its so-called dual object, right? So the coefficient of the sine of the tangent, okay, so the coefficients of a power series is determined by this function f of x. So if you want the series, if you want information of the series, and not the series but the sequence, right? If you want information about the sequence, you can, in principle, get it from the function f of x. So generating function is this amphibian between the discrete and the continuous world. And the analysis of generating functions typically requires some sort of theory about analytic function, which then calls for complex variables. It's very interesting. General formula for the expansion coefficient calls for Bernoulli numbers. And if you want to see the formula, which I can't recall at this moment, you can go to a website by not a website, but I think it's open source nowadays. I won't get into trouble for showing that. There's a handbook of mathematical function and table called Abramowitsch and Stegen. Abramowitsch and Stegen, yes, this one. And this is also a great piece of math history, handbook of mathematical function. So many of the calculations done in this table. So basically, it contains formulas, tables, not just formulas, okay, but also numerical values. Because back then computers aren't widespread. If you want to calculate a log, you would use a log table. If you want to calculate a trig function, you would use sine and cosine tables, things like that. So these were calculated, systematically calculated during the Great Depression and the Second World War, because a lot of highly educated people back then, I don't know why it's so slow, huh? Perhaps close some of the tabs. Yeah, so these tables were compiled, partially funded, I think actually mostly funded by the US government during the Second World War. Right. So Leo, he just published a video on the history of computing, and in particular generative AI. He knows a lot about the history of computing than I do. But here in this table, in this source, I don't know why it's so slow, man. This is used to be a must-have for every applied mathematician or scientist, engineer. And nowadays, they are mostly digital, or they exist in the back end of softwares like MATLAB, NumPy, SciPy. that sort of thing. Oh, hi, Hiroshi. Hi. Yeah, I was just talking about if you want to see a full expansion of the tangent, and typically you would go to this book right here, Abramich and Stegan, and it not only includes the formulas and expansions and tables for elementary functions, but also for specialized, actually just called special functions in mathematical physics. Things like Bessel functions, gamma function, lots of these monsters there. It's very interesting piece of math history. And a lot of people who participated in the project were actually women. Because, well, men were needed for the war effort, for the more hazardous job. So Irene Stegan was, she was the leader, one of the leader actually. Unfortunately, Abramich passed away early, as far as I know. You can look them up. Very interesting math history. Milton Abramich passed away early, and later on, Irene Stegan led the effort. So, speaking of the tangent expansion, for example, you typically don't do that by hand nowadays, but still, it's good to know what's the fundamental way, what's the fundamental principle to obtain these coefficients. But typically, when you actually need those coefficients, you go to sort like that, or nowadays you just AI, the answer to all of your problem, apparently. So here, you got elementary transcendental function, page 65. Just sheer awesomeness in this book. Just centuries of intellectual effort condensed in 470 pages. So, and just awesome. Where's the tangent function, man? Here we go. Exponential, I guess, and you got more trig, I guess. Trig, yeah, circular functions, sine and cosine are defined in terms of complex variables. Yes, and this is something we'll see. Sine and cosine are defined in terms of complex variables. All right, so this is just some trig identities. Here we have more special trig values. Yeah, series, finally series. See, this is the full expansion. So we just calculated the first two terms, z and z cubed over 3, right? And if you want to do this in general, you want a general expansion coefficient, as you can see, it's quite complicated. You would need, hold on a second, is that right? Is that even right? Is it an alternating series that I didn't know about? Huh. I mean, this probably should be right, with a high probability of being right, but actually, perhaps I don't know enough about the Bernoulli numbers, okay? So the Bernoulli numbers might be negative, actually. Let me just quickly search that. Bernoulli numbers. Bernoulli numbers. Yeah, there's negative in the Bernoulli number, so this solves the problem. Okay, the series itself is not alternating, even though it was a -1 to the n minus 1. So b2n is, hold on a second, b2n is all. Oh, actually, b2n oscillate. So b2 is 1/6, b4 is -1 over 30. Yeah, it alternates, so it works out. So the series itself is not alternating. Okay, so that's the general coefficient. Here, did it say b2n? Yeah, bn are the Bernoulli and Euler numbers. Bn is Bernoulli numbers, En is the Euler number. So these are in the later chapter of the book. Okay. Actually, yeah, here as you can see, I mean, in later part of the complex variable series, we will see what these means. Okay, how do you get the infinite product like these? And also expansion of partial fraction. So these are all results in complex analysis. And here is just the final product of them. Okay, and they're actually quite deep theorems regarding them. Euler first solved the famous Basel's problem, the sum of the reciprocal of all perfect squares, using this expansion. But back then, complex variable theory did not exist yet. So Euler's method was, although ingenious, it wasn't fully rigorous. Because actually one of the many reasons to rigorize some of the giants' work, like Euler, Laplace, and whatnot, so they have great intuitions, although their methods aren't always secure, and sometimes they lead to contradictory results, which was the main motivation to develop analysis. Okay, develop rigorous analysis. Anyway, so showing sine. Yeah, this is very deep. Yeah, sine and cosine, they're very deep functions. They can be, one of the most. Just a meta commentary. Like one of the most, I would say, fascinating aspect of learning mathematics is that notions can be approached from so many different levels, right? When you see sine and cosine in high school, you learn it from a triangle, right? And then you can appreciate these notions at various levels, okay? But unfortunately, this also creates space for snobbery. So let's say if you're a high school kid and you just learn the sine and cosine from a triangle, and some asshole from an elite university tells you, you don't actually understand sine and cosine. You have to define sine and cosine either using infinite series or a complex number, right? And they're just doing it to sound smart. Like, let's be honest here. They're just doing it to sound smart. There's absolutely nothing wrong if you know a notion from a particular approach. Of course, it's just appropriate for the level of study, right? It's completely unfair to say, if you only see sine and cosine from a right triangle perspective, you don't understand it. Like, it's such a, in my opinion, silly thing to say, right? So, but still, that set aside, is the fact that mathematics can be approached from so many different perspectives is amazing. It's somehow all these wildly different objects, seemingly wildly different objects, miraculously stitched together. So that's one of the greatest enjoyment, based on my experience, to study mathematics. Right. So there we go. Let me. That's a digression. Let's come back to the main topic. So that's a good piece of reference. Abramich and Stegen. Also, a great piece of mathematical history. Abramich and Stegen. You can see this got his own Wikipedia page. Milton Abramich, unfortunately, died a little bit early, before the book could be published. So the book was compiled after the Second World War, even though the bulk of the work was done during the Great Depression and the Second World War. So a lot of it was classified information. Not classified, but still not easily accessible, right? So, the elementary functions aren't secret, but to access the values of them quickly was not something that's always easily done. So there you go. And Irene Stegen, she led a long life. Anyway, coming back to complex analysis. Okay. And yes, a lot of people just say a bunch of blah, 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 and the purpose, if it is to be instructive, is not fulfilled. Yeah. Anyway, so let's come back to complex analysis. We were talking about examples of analytic functions. So the first class of functions that are analytic throughout the real line later on will be called entire. These are entire functions. So these are, in a sense, the kind of function that is closest to polynomial. Okay, and then we have the rational function. The rational functions, tangent, blah, 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 and so on, will later on be categorized as the so-called meromorphic function. Meromorphic. So this later will be generalized to so-called entire functions, technical terminology, and these groups will be generalized to so-called meromorphic functions. Okay, in a complex analysis context. Okay, meromorphic function. All right. Meromorphic, I believe, is a word that stemmed from Greek. It's like fraction-like. Mero, yeah, Greek partial. Meromorphic is. Uh, Shout out to my complex analysis. Yes, yes. Mero is like meromorphic come from Greek. Although I didn't know it means partial. Okay, but thank you so much, Leo. A complex analysis professor saying this. Awesome. Leo, how many courses have you taken? Like I thought you were mostly a computer scientist, and I mean, I guess because of cryptography, you probably took analytic function. Sorry, not analytic number theory, right? So you need complex analysis. Man, you're so knowledgeable, man. That's insane. How do you know all of this stuff in math? It's crazy. I was just watching your documentary. So guys, if you haven't still watched Leo's documentary on the role of AI in math, so go check it out. It's a very, I should say, it's documentary level, professional documentary level content, man. Just go check it out. Massive amount of work was put in there, and I never learned this in my university and whatever. So yeah, it was crazy. Yeah, elliptic curves does have a lot of complex analysis, exactly. Well, I sit in this class, I didn't officially take this. You want to be kind of general knowledgeable in math and computer science, you talk about it, etc. I see. I see. Yeah, I didn't do that enough, actually. I didn't do that enough when I was in the uni, regrettably. So I was just kind of a nerdy guy, just do his own thing, and didn't really care what other people were talking about, and just quite frankly living under a rock the whole time, which is a shame. Don't be like me. Are you on vacation? Yes, I am currently. Thank you, Hiroshi. That's why I have time to do multiple streams a day, like a jobless loser, But yeah, I'm on vacation. But seriously, I mean, that's too harsh. If you're unemployed, you know, Einstein was quote unquote a jobless loser for a long time. Don't let your current employment status dictate your value. Okay. Very uncomfortable living under rocks. I know, right? I know, right? Living under rocks sucks. I don't know why I did it. Just young and ignorance, I guess. Being young and ignorant. Don't be like me. Stay connected with others. Anyway, so coming back to the topic of analytic function. So there you go. So let's give another example. Natural log of x. A natural log of x is analytic. Okay, let's not promote negativity on this channel. Okay, math is already difficult enough. There's no need for this kind of nonsense going on here. I took the blame. Okay, I'll stop using that word. Natural log of x is analytic inside the interval 0 to infinity. Inside 0 to infinity. Well, you know what, guys? Let's do a general example. So before here, we've only expanded the functions at the base point x equals 0. Why don't we do so? Why don't we do a general expansion for the natural log of x? So I think that would be important because you don't want to have this kind of mental inertia that whenever a power series is written is always in the power of x. Well, it could be in the power of x minus x naught. Yeah, I'm not in the toxic positivity, right? I just don't want to add unnecessary negativity. I don't want the hierarchy, I don't know how do I put this, but basically, I don't want positivity for its own sake because I never said on the channel, I said, oh, everyone is a genius, everyone can be a mathematician, that kind of thing. I never said that. I never said that. I mean, it feels so cheesy to me to say that kind of thing because seriously, not everybody can be a mathematician, and not because of intelligence. Okay, simply, I think the most important reason is priority. Okay, I mean, we're going on a digression, so I take full responsibility now. So I was saying that not everybody can be a mathematician simply because of priorities in life, and sometimes just unfortunately because of social stereotypes and that kind of thing. Let's say, of course, math takes a lot of time. I mean, I'm the living proof, right? I do math like 10 hours a day, minimum, like right now. But still, like, the point is, math takes a lot of time. And, even if I spend that amount of time, like, where are we in Measure Theory right now? We have like tens of hours of time spent on Measure Theory alone. And I'm just in the first half of chapter 1. And I don't think we spend a whole lot of digression during those sessions. It takes a lot of time. And let's say if you want to prioritize other activity, that's certainly justifiable. Let's say if you have a sick family member to look after. Let's say if you want to serve your community more. Right? I'm not promoting like academic obsession above all else. Right? But I would not take saying I'm not a math person seriously. Unless you have a medical certificate that says you have some kind of mental cognitive disability, right? In that, unless for those sort of situations, because I'm not medically qualified to discuss that kind of thing. So unless in those situations, I simply will not take not a math person as an excuse. You can have other priorities, that's for sure, but don't say you're dumb, because that is statistically very unlikely to be true. Yeah. Okay. Do you like math? I mean, well, do I like math? It's hard to say because I haven't been following his stuff for a long time, right? So I just noticed that he stopped putting out actual math. I'm a guy who likes to do actual math. If you can't tell already, right? Most of my videos are about actual math or actually doing actual math, right? I used to have book review videos, and those were undoubtedly actually inspired by math sorcerer. But later on, I just got tired of it, and I don't want to say some generic thing about a book because it feels disrespectful to the author. They spend so much effort to say on this work. There are so many details being added to emphasize their insights and whatever. I'm just flipping the pages, say, oh, this picture looks nice. Oh, the font looks pleasing. Okay, that's so superficial, man. I don't want to do that. So these live sessions actually kind of evolved from this is book review essentially. This is book review. This is actual book review. Even though I can't show you the book because of copyright and stuff. This is actually the next evolution of my book review videos. I stopped doing book review videos because I find them uninteresting. Right. I reached this stage that I just don't want to vaguely talk about a math book and move on to the next one. I mean, math it's hard. It's hard to appreciate math. Let's just put it this way. It's not like you look at a piece of painting and you can get an immediate reaction out of it. Right? It takes time to appreciate, and you can't really say anything really in a 5-minute, 10-minute, or even 20-minute video, an hour at least. Okay, if you want to do a serious math review video, in my opinion, I mean this is hot take probably, you need an hour to do that, to say something that actually why this book is worth reading. Right, so it's and some still at the same time makes it more accessible to a general audience, right? More not to say general audience, just to people with higher mathematics literacy. You still need time to explain why a certain book is interesting, right? What it brings to the table, why you like it, right? Not just the picture kind of looks cool, and other stuff. It's got such a cool vibe to it. I mean, what's the point there, right? So, do you have a chance to read that book by Russell? Unfortunately, no. So there you go. Once again, I mean, I'm not trying to poo-poo on Master Ulcer. It just I feel like what we're trying to do is different. Like he can certainly do his own thing. It's his own channel, and he has a lot of followers. A lot of people are inspired by him, which is great, But this is what I do. Okay, this is what I do. And previously, I know Master Ulcer, he used to have super like mathy stuff. Let's just put it this way. He had entire courses on differential equations and like proof writing, set theory, and what's that? Calculus, right? And they're awesome. They're completely awesome. And nowadays, he seemed to be stopped doing that, which is, I mean, I'm a little bit disappointed, but that's entirely his decision. He it's his channel after all. Like if I see a creator and I like what he or she is doing and I follow, if I don't like, I just stop following. As simple as that. It's a free world. Right. All right. So. Yeah. Oh hi. Oh hi, Wriggles. He wrote 40 books in 1 month. Well, I don't want to get into that. I mean, this is a one-man. I mean, talking about. I mean, on this channel, my channel is a one-man operation, and is I have no editor and no PR people. I'm just one guy, and I cannot afford drama, distraction, that kind of thing. I just don't want to get into that. Like he can do whatever he wants. Okay. All right. So. X, natural log of x is analytic inside the interval 0 to infinity. Let's see how. Let's actually give a general proof. Let's actually give a proof for this. Okay. Anyway, so to fulfill that goal, to show x is analytic inside the interval, so why don't we start by letting x naught to be a point in 0 to infinity. We need to show that the natural log of x has a power series expansion of the form given in the definition. So you need to expand the natural log of x in this format. So how do we do that? Well, let's use a fact. Recall, we do have a series related to the natural log, but it's for natural log of 1 plus x. Natural log of 1 plus x is the sum. Actually, let's write first few terms. This is, by the way, the function. Draw a picture right here. Minus 1. Like that. Okay, so near x equals 0, the first term is actually 1. Is actually not 1, but x. Is x minus x. Actually, I can't remember the series very well, but I think it's x minus x squared over 2 plus. Actually, you know what? Let me just do some scratch work because I can't remember. Sorry about that. Well, start from the geometric series. 1 over 1 plus x. That's the sum of minus 1 to the n, x to the n, and goes from 0 to infinity. Right? And then you just integrate on both sides. So integrate, you get 1 over 1 plus x dx. And on the right, you got plus c, put it on the front, plus c, and term by term integration. And by the way, this will be rigorously justified in a complex analysis context. Minus 1 to the n, x to the n plus 1 over n minus, actually n plus 1. So on the other hand, we know, say, actually, you know what? Let me do from 0 to t, shall we? From 0 to t. Let's do a definite integral on the left-hand side. This way, the right-hand side would be the series sum over n. N goes from 0 to infinity, minus 1 to the n, x to the n plus 1 over n plus 1. And the bonds are 0 to t. this way, just the sum of n from 0 to infinity minus 1 to the n, t to the n plus 1 over n plus 1, all right? And you got the sum of n goes from 1 to infinity minus 1 to the n minus 1, t to the n over n factorial. And we also know that this is just the natural log of 1 plus t. So we got the series expansion. Okay, so anyway, yeah, now we have the series expansion. The sum, we have this series expansion that's true for, actually, we'll come back to the convergence thing. We'll come back to the convergence thing, which is actually one of the motivations for complex variables, actually. So this is the sum of the terms 1 minus 1 to the n minus 1 t to the n over n of, oh, not factorial, I'm not doing. There's no factorial, just over n. The convergence is not very fast for this series. T to the n over n goes from 1 to infinity. Yeah. Oh, can you cover the book The Remarkable Sine Function? Wow, you know that one, huh? Man, you guys are amazing. You know that book. It's a great introduction to elliptic function. Yes, absolutely. It has so little prerequisites, and it's a great introduction to elliptic function. Exactly. Markushevich was a wonderful writer. I wish more people in the West know about him. It's also published by Mir, the book. Mir is such a gem. Mir is the best legacy of the USSR. Anyway, so when you write a series like that, you should always pay attention to the interval of convergence, or at least the radius of convergence. Okay, so here the series that we obtained, okay, is the geometric series from which we obtain our series. We use the geometric series. Oh, sorry, that's terribly phrased. We use the geometric series to derive the series for the natural log, and the geometric series converges on the interval x absolute value less than 1. Okay, so Mech, actually, you know what? Because of you placed the request, I'm actually going to put it in my to-do list. Put it in my to-do list. All right. Because this is, by the way, guys, this is the upcoming stream. This is the upcoming stream, man. The to-do list just keep growing. Financial math, I want to wrap up the Markovich frontier derivation. Information theory, I want to wrap up the sufficient statistic. Shout out to Leo for bringing my attention to this topic. I want to wrap this up. Optimal control theory, I want to see a complete example of the Pontryagin maximum principle. Hawk's process, fluid mechanics, option pricing, SDE, algorithmic trading, and now we have another item that's the remarkable sine function by Markushevich. Thank you for mentioning this book. It's such a nice little read. All right, and a book by Harris Hannock. I'm not sure. Let me just put it here. Okay, Harris Hannock. What's the name, Hiroshi? Harris Hannock. Hancock. Okay, what's the name of it? Hiroshi, if you don't mind, please let me know the name of the book in chat. And James Koenig said, "Hello, Mr. Ming. I'm in Calc 2 and just finished up series and love mathematics. Any recommendation to teach myself Calc 3 and 4 onward?" Okay, so yeah, I mean, if you lectures on a theory of elliptic function, wow. Oh, that's a classic. Actually, I remember. My goodness. I mean, I didn't read it, but I know this book exists. Lectures on the theory of elliptic function. Hiroshi, in case you guys don't know, show up a lot in my stream and mention all kinds of British texts. Okay, like we just lectures on Hannock's book on elliptic function. I don't know, actually. Hiroshi, actually, I don't know, because I'm not well versed in the area of elliptic function. I prefer a more modern introduction on that topic, and when I get perhaps a passing familiarity. After I get a passing familiarity, I'll come back to more classic treatment. That's just how I usually do things, because I tend to do my first study on more just well-known books. Okay, I know it's superficial. I know it's superficial. It's like clicking the video with the most view already. Right? I just find learning things that way gives me better chances of getting help when I'm stuck. All right, so that's the okay, yeah, okay. Anyway, we'll actually do some. I mean, I wouldn't call it legit, but just perhaps more widely known method in algorithmic trading. I'll just give my own opinion on it. I'm not a professional trader or anything. I'm just presenting the topic as it is. Actually, I'm very new to this as well, so don't take my words as with a great grain of salt, because did I spell it correctly? Anyway, it doesn't matter. This is the new to-do list, which just grows every day. Okay, so our life is very short. Anyway, coming back to James Koenig's question. Sorry for skipping that question. I mean, book recommendation. I mean, I don't know, man. You can't just do Stewart. Stewart is okay. It really depends on what you want out of a Calc 3 course. If you want to say, if you really love mathematics, and I think it's a great. I mean, I'll give you two. Okay, I'll give you two for Calc 3, rigorous Calc 3, and more general Calc 3. At James, for Calc 3, I have two recommendations. For Calc 3, for general purpose, okay, general purpose. I mean, general purpose don't mean lowbrow. Okay, it's still important skills, and especially if you're, say, work in applied field, you should be able to crunch out numbers like there's no tomorrow. Okay, so general purpose book, just go with Stewart. I mean, I know it's unimaginative, but it's actually a great book. Guys, I put my exercises, like not exercise, but quizzes, out of, I design many of my calculus quizzes. I mean, I do quizzes in several subjects, right? But for the calculus quizzes, my main reference is actually Stewart. It is a rigorous book. It is a rigorous book. Even though it doesn't have all the proof, it says, okay, this needs to be proved, and we're not going to do so here. It doesn't pretend that it has all the proofs. But the book is actually rigorous. James Stewart, and it's very approachable, has lots of exercises that build your confidence, and it has interesting projects, which I don't think gets mentioned enough. James Stewart, text. Calculus Early Transcendental, and for more rigorous treatment of Calc 3. You mean typically Calc 3 is multivariable stuff, right? Multivariables, what's that? Vector calculus. That's typically the content of Calc 3. Yes, Stewart's is pretty solid. It gets a bad rap. Once again, I suspect from those people who say, oh, you don't understand sine or cosine unless you define it using an infinite series or complex numbers, and call people who only know sine or cosine from a triangle, like, don't understand the function. I mean, it's just the pure snobbery. It's not worth taking seriously. So anyway, for Calc 3, for more theoretical treatment, for Calc 3, more theoretical slash proof heavy, okay, use this one called Functions of Several Variables by Fleming. Functions of Several Variables by W. Fleming. Once again, just absolute classic by W. Fleming. I don't know nowadays this is still well known, but basically I believe even in texts like Baby Rudin, the multivariable portion of Baby Rudin cited this book, actually. Let me just check real quick. I have my Rudin next to me. Was it quoted? Oh, no, I don't want to. Yeah, actually just one M, my bad. Fleming. It's just one M, not two. W. Fleming. It was listed in the bibliography of Rudin's principle of analysis, principle of mathematical analysis, for more rigorous Calc 3 treatment. Also, even despite the intrinsic difficulty of the book, it has lots of exercises that are approachable, which is great. So there's a Calc 3 on steroids. All right. So here. Oh wow. Hiroshi said, I discovered in Hancock's book that the formula for calculating the max value of a function of two variables was wrong until the beginning of the 20th century. Yeah, it can happen. It can happen. Like math books aren't always correct, right? Aren't always correct. This is part of the, just the natural part of doing mathematics. All right. So anyway, I think I'm all caught up with chat. Okay, I started with Calculus for Practical Man. Yeah, Calculus for Practical Man was the book used by who's that? Feynman, Richard Feynman. It's a great book. Yeah. Once again, the choice of book isn't that important. I mean, I'm just giving out book that I find useful. That's the whole purpose of it. I'm not saying, oh, this is the best book. Okay, I'm not never making that claim. I just say these books helped me, and I like them. I'm attached to them. All right, and it is biased, but that's just my opinion. You ask for my opinion, I give my opinion. Right. So, and my opinion strongly lean towards that it does not matter which book you choose to study, but whatever you choose to study, try to internalize it. Right? And by that we mean you feel that the concept is almost inevitable, as if you could be independently discover it. And this is how knowledge sticks. Right. The book is titled Theory of Maxima and Minima. It discusses piano function, which serve as a counterexample formulas in the book. Okay, great, awesome. Thank you so much, Hiroshi. Love it. I love when people. Actually, you know what, Hiroshi, I strongly recommend, if you haven't already, join the Discord server and just talk about these things in the Discord chat, because the stream chat, of course, I mean, it is archived and whatnot. I just feel like on Discord you can post pictures and other things. If you haven't already, I strongly recommend. Once again, no pressure whatsoever. If you want to, only if you want to. Yeah, this kind of discussion is the one I wish to see a lot in my book recommendation channel on Discord, because these are discussion about books that have substance. Okay, what's great about it? Is there any mistakes? And whether things I move on. Saying, oh, this is such a great book doesn't really help a lot of people, right? Because reading a book really is a massive time commitment. Like, you have to give people a reason why they should give a toss. Okay, sorry for my French. So that's my little rant, or yeah. Okay, anyway, so I was saying, like, here, going back to the actual math, the geometric series converges when the absolute value of x is less than 1. Okay, it is a result in real analysis, actually. In real analysis, that term-by-term integration is permitted in the interior of the interval of convergence. So, yeah. It does not guarantee whether the behavior of the series at the endpoint of the interval is changed. Okay, so this is actually a good example, because we know the original radius of convergence is 1. After term-by-term integration, that hasn't changed. So the series is still convergent when f absolute value is less than 1. This is still true. This is still true. However, the boundary behavior may change, and we simply ignore the boundary points. Okay, the boundary points can have wildly different behavior actually. What's interesting is that in complex analysis, the behavior on the convergence disk, the boundary of the convergence disk, is essentially a Fourier series. It's essentially a Fourier series, and the Fourier series has wildly intricate convergence behavior. So for the sake of avoiding intricacies, we're not going to look at the behavior at the endpoints throughout the most of the discussion in complex variables. Okay, we're doing analysis on open sets. All right. So here we're saying that if you plug in t equals say 1, if you plug in t equals 1 in the series is still convergent because of the alternating series convergence test, the alternating series test. If you substitute if you substitute t equals 1 in a series, it's still convergent. So it's convergent on at least one boundary point, t equals 1. So when I say t absolute value less than 1 after the series, I know I mean on this interval, on this open interval, the series is guaranteed to converge. But we're just not talking about what happens on the boundary. When t equals 1, this is indeed convergent. It is in fact conditionally convergent. When t equals -1, however, the series is divergent. So the actual interval of convergence for the natural log of t, 1 plus t, is semi-open. So it's the interval of convergence is would be it does not include -1, but includes 1, as I was saying. If you plug in -1, the series is the harmonic series, or it diverges. So term-by-term integration guarantees that the radius of convergence stays the same, but it does not guarantee the behavior at the boundary stays the same. The series, the original series, namely the geometric series, diverges at both endpoints. Diverges at both endpoints, at -1 and 1. But here, after integration, suddenly it is convergent at one endpoint. You simply cannot control this kind of thing. You have to do it on a case-by-case basis, which is a little bit annoying. Anyway, so here I'm just going to use the series here and say x absolute value less than 1, which is no problem. This is certainly true. And what we care about only needs open interval. Only needs open interval. Analytic on AB, if for every x naught in the set AB, in every set A to B, on some interval of x naught, some neighborhood actually, some neighborhood which is an open set by definition, the series convergent and equals f of x. So this is what we needed. And now it's just a matter of an algebraic trickery. So write the natural log of x this way. So you got, I want to get an x naught in the expression, so x plus x naught, and then plus x minus x naught. All right. And then I'm going to factor out x naught inside the natural log. So x naught times 1 plus x minus x naught over x naught, like that. And use the law of logarithm. You get the natural log of x naught plus the natural log of 1 plus x minus x naught over x naught. And now you just apply the series. So this way you get the natural log of x naught plus the sum, all right, plus the sum of -1 to the n minus 1 and x minus x naught over x naught raised to the n divided by n. Let's not forget that factor here, divided by n. Actually, you know what, I'm just going to write it as the format that we wanted in this series. -1 to the -1 to the n minus 1, yeah, and over n, x naught to the n times x minus x naught to the n. Right. That's the form that we wanted. N goes from 1 to infinity. And when this is true, take a look. Here we need the variable x minus x naught over x naught to have absolute value less than 1. So this is true when x minus x naught over x naught absolute value less than 1, which is the same as or x minus x naught absolute value less than x naught. Remember, x naught is positive, so you can get rid of the absolute value sign. So that's exactly what we wanted, right? So look at the interval from 0 to infinity. Here, x naught is our expansion point. The final result says at x naught we can find a neighborhood. That's the neighborhood, right? The neighborhood is centered at x naught with radius x naught. This is exactly a neighborhood. On this neighborhood, the series converges and is equal to the natural log of x, which completes the proof. All right. Guys, I just need to use the bathroom real quick. I'll be back in 2 minutes. All right. Coming back to do more math. Okay, so that's another example. Okay, so these examples, they all have their counter and no, sorry, not counter example, but counterparts in complex analysis. So the entire functions, that's the first group, and you have the meromorphic function. And the natural log of x is very special. The natural log of x, later on, as we will see in complex analysis, is an example of so-called multivariate function, or sorry, multiple valued function. And it has something to do with the so-called branch cut. So the function natural log in itself can have multiple values that are valid. So which is a little bit odd, because by the modern definition of function, the output of a function should be uniquely defined. But the natural log really, it should be a multiple valued function. Multiple valued. Even though the notion of multiple valued function might sound a little bit odd, but if you think about it, you already seen this in elementary algebra. So if you want to solve the equation y equals x squared, then x would be, let's assume y is non-negative, okay? Then x would be plus or minus square root of y. In high school, you're told that this is not a function. Right, so imagine now you have the inverse, quote unquote, y equals plus or minus square root of x. This will be the inverse function of y equals x squared. And you're all told in high school that this is not a function because it fails the so-called vertical line test. So how do you make that a function? Well, you pick a branch. You pick a branch, you pick up the upper branch or the lower branch, and by default, square root of x refers to the quote-unquote the positive branch or the principal branch. But at the end of the day, this is an arbitrary choice. There's no reason that the other branch is somewhat less mathematically valid. Right? So the idea of a multiple valued function is already present in elementary algebra. And at the end, not the end, but in the more advanced section of the book, here, actually, do I have here? Perhaps I'll show this in a, just for the sake of, here, going back to the list of content. There's this chapter on Riemann surface. So the idea of multiple value function gives birth to the idea of Riemann surface. We were going to study these functions, sine and cosine, entire, meromorphic, and multiple value function on the complex plane. But as it turns out, that the natural domain for functions like the natural log of x isn't the complex plane. It's instead on a Riemann surface. So my understanding for that is still very limited. Okay, so these are just my TED talk. Okay, not actually I'm a master in that. It's just a vague understanding for that. It's like you can force. You don't have to force. In fact, you don't. Here in this artificial construction, you force the function to pick one value, right, which is fundamentally arbitrary. But there are ways to make the functions to take single value, provided if you rethink their domain and codomain. Okay, so this is pretty interesting. Multiple value function, which leads to the idea of Riemann surfaces. It's a hugely interesting area, Riemann surfaces, which connects complex variables with topology. All right, so let's continue with the actual math. Just join. How is this resource different from Western book? Good question. It's just the depth, I think. The depth and thoroughness. And the fact that this one and also the other one I mentioned from the earlier part of the stream, the one by Tikhonov and Sveshnikov, are both representative of Russian-style complex variables. It's just that, to me, that the Russian texts are more motivated and more thorough, and is connected to the classical tradition a little bit more. And even though the texts are relentlessly rigorous, they do not pursue abstraction for its own sake, and they pair rigorous proofs with deeply intuitive commentary. I mean, complex analysis is such a mature field. It's hard to have wildly different approaches, right? Let's just be honest. But I like these books because they feel to me very refreshing. They feel to me very refreshing, and they like to motivate things and like to emphasize a deep connection between various branches of mathematics. Although perhaps for a beginner in the subject, you're better off just use the Brown and Churchill, and if you decide you like complex analysis, you can check out the more like these. So because another reason is that the Russians tend to put exercise in a separate text, which is inconvenient for beginners. Right? So this is just how they do things. Anyway, all right. So actually, what we're saying is this part actually serves as a motivation. This is chapter 0. This is chapter 0 in Markushevich. Okay, this is chapter 0. This is just for motivation. They don't just give the definition of complex number right from the start and start pushing the axiom. This is part of the motivation by Markushevich. Why do we care? Okay, by Markushevich. This is chapter 0. Okay. Once again, perhaps a little bit of a personal opinion. I reject the notion or the practice of saying, "Oh, you should learn mathematics because it is beautiful." Like, to me, that doesn't seem like a very convincing argument. There are many beautiful things in the world. And many beautiful things in the world don't require intense suffering to appreciate. Why should I be bothered with mathematics? To me, that seems like a rather shallow explanation. And why is it beautiful? Right? So, I think the best way to motivate is to connect whichever mathematics you're trying to sell with the existing knowledge of the target audience and tell them what they can gain from it. Right. So that would be my approach. And telling someone something is beautiful itself, the act of doing that sounds a little bit odd, because let's say if you look at a piece of beautiful painting, listen to a beautiful music, you don't say, "Oh, this is so beautiful." You just enjoy it. The beauty is obvious. When you spend so much time telling people that math is beautiful, that act in itself is a little bit odd, because somehow beauty needs to be reminded. My point is that it doesn't. It doesn't, and there are ways to so to say, to make. There's no need to dumb down mathematics. People are inspired to do hard things. We all do. The solution is not to make math more easy, make it easier. Let me learn complex analysis in 5 minutes or in an hour, for that matter. It's not that. People are attracted to difficult things, and you just need to give them a reason why they should care. And the Russians do that. Okay. Anyway, let's continue here. The sum, difference, product of ratio of the analytic functions are analytic functions. So this is, here it's just stated, but this will come up later in the course, and we'll do things in a complex setup. So the sum, difference, okay, this is a fact, in real variable theory. We're not going to use that. We'll develop the complex counterpart along the way, but it is a property that the analytic functions is closed under sum, difference, product, and ratio. Of analytic functions are still analytic. Provided the domains are appropriately defined. Okay, so for example, let's say you divide sine by cosine, you get tangent, right? It's not an analytic function everywhere. You just need to restrict the domain. You just need to restrict the domain to an interval on which tangent is well defined, then it is an analytic function. Right? And speaking of which, this tangent function I forgot to mention, because this is actually a great opportunity to motivate complex variables. Right? So let's say you calculated the series. Right? We've seen the general series in Abramowitsch, and Stegen here. Right? We've seen the general. I hope it doesn't take nearly as long time to load. Maybe it will. My goodness, it will do that again. Anyway, I was saying that you can have the general series. You can have the expression for the general series, but the question remains, does it converge? If you let's say, if you derive the formulas for the general term, how do you know it converges? And when it converges, does it converge to the tangent of x? It's not a trivial question if you think about it. Come on, give me the formula. Well, it's 25%. But basically, my point is that in general, we've seen that earlier, that the formula for the coefficient of the tangent expansion requires Bernoulli number, and it's quite complicated. So let's say you have the series calculated. Let's say you wanted to find the radius of convergence. How do you do that in calculus? Well, you do that using a ratio test. Like here, for example, let's say you wanted to calculate the radius of convergence of the natural log of 1 plus t, right? The radius of convergence for the natural log of 1 over t, the radius of convergence for the Maclaurin series of this function. Right? What do you do? In calculus, you do the ratio test. You take the ratio between consecutive terms, take the absolute value that n tends to infinity, and see when the ratio is less than 1, because that's the condition for convergence in the ratio test. And then you solve for t. Solve for the range of t. That's how you find the ratio, the radius of convergence in calculus. However, it's not so convenient, is it? Because of the expression for the general term of tangent is rather involved. It's complicated. It involves the Bernoulli numbers. So you got to study, what are the properties of the Bernoulli numbers to figure out the radius of convergence. So that's annoying. Do we have that? Okay, anyway. So yeah, that's annoying. So if you, let's say you use the general formula for the coefficient in tangent to determine the radius of convergence, it will take a lot of work. But even after that's done, the harder question remains. Do you have to pay to subscribe? No, you just click subscribe. Yeah, so the thing is, even after, let's say you did all that work, you find the general term using the Bernoulli number, and you do the ratio test, and you figure out the radius of convergence. Another question remains, how do you know the series converges to the original function tangent of x? Right? Just because the series is convergent doesn't mean the sum has to be tangent of x. There are counterexamples for that. You have a convergent Taylor series, or power series, but the series does not converge to the function that generated the Taylor series. There are odd examples of that. So this is the harder part, even harder than the calculation of radius of convergence. And actually, this is still considered to be a lucky example, because still, at this point, tangent of x has a known expansion. You need these fancy numbers to do that. Imagine, let's say you have more complicated, say tangent of x plus the square root of tangent of x. My goodness, the natural log of tangent of x. This is a common function. But back in the days, a lot of table for tangent was actually in the form of the natural log of tangent, because tangent blows up rather quickly. So you use the logarithm to tame the growth. What about the log of tangent of x? You can't really get a nice expansion, can you? It's difficult to do that. So the recipe given by traditional calculus is very difficult to use. Right? In traditional calculus, you calculate the expansion first, and then use the ratio test to determine the radius of convergence, and then you have to establish the series actually converged to the original function that generated the series. It is very difficult. However, as we shall see in complex analysis, all you need to do is simply to locate the singularities. So we know intuitively that cosine has zeros at, well, half pi, minus half pi, and so on. 3 pi over 2, and so on. So with the power of complex analysis, with the power of complex analysis, what you need to do is just the following. You look at the expansion point. The expansion point is 0. Right? The power series is obviously expanded at 0. And you see where the nearest singularities are. The singularities of tangent are plus or minus pi. And that's it. That's it. So that's the radius of convergence, just from minus to just half pi. And that's it. That's literally it. You don't need to even know what the series looks like. You don't even know the first few terms, let alone the general term. You just look at this function. Okay, you just look at this function, say, if you expand the series at a point, say x equals 0, what would be the radius of convergence? Simple. Just find the distance between the point of expansion and the nearest singularity. That's the radius of convergence. And that's the power of complex analysis will give us, okay, among many different things. Okay, so yeah, hopefully this is a good motivation for why complex analysis makes your life easier. And let's continue. Okay, so now let me see. Yeah, this is a table, right? This one. I mean, doing the ratio test on its own wouldn't be such a terrible. I mean, it is still complicated because even though you have cancellation with these factorial things, right, and the power of 2 to the 2n, you still need properties of the Bernoulli numbers to actually do the ratio test. Right here, this radius of convergence, absolute value of z less than half pi, is determined by the method stated earlier. We just look at the singularities of z, of the tangent z. That's good enough for you. All right. So these are the great rewards of complex analysis promised here. Okay? Anyway, let's go on with the main text. The sum, difference, product, and ratio of analytic functions are analytic provided the interval provided the inside an interval where the denominator do not vanish. Okay, let's put that here. Inside an interval where the denominator don't vanish. Okay, this is a fact. And also the derivative and integrals of analytic function is analytic. Right here we've seen an example for that. How you get the series expansion of the natural log from the geometric series. So this is a technique that works in general. The derivative, so first of all, analytic functions are differentiable and they're integrable. The derivatives and integrals of another fact, okay, another fact, derivative and integrals of analytic functions is analytic. Are analytic, okay. Also very useful fact, you know. So, all right, here, and this is an interesting fact, and also highly non-trivial. It says the following. So if the functions, hang on, functions aj of x, where j goes from 0, 1 all the way to n, are analytic, then the solution of linear differential equations whose coefficients are aj's is also an analytic function. Then the function defined, the function f of x defined by the differential equation, so a0 of x plus a1 of x times f of x plus all the way to an of x times the nth order derivative. Oh, actually, you know what? Sorry, the first example is actually algebraic equation. My bad. The first equation is algebraic. That is a1 of x times f of x plus all the way to an of x times f of x to the nth power equals 0. F of x defined by this thing, this is an algebraic equation. Of course, this function isn't defined implicitly. Unlike earlier examples where you have an expression for f of x, here the function is defined implicitly by an algebraic equation, and also by differential equation, which is a0 of x plus a1 of x times df over dx plus all the way to an of x, that's the coefficient for the nth order derivative, dnf over dx to the n equals 0. Also this is a differential equation, linear differential equation. It's called an nth order. Okay. Using differential equation jargon, it would be the nth order linear homogeneous differential equation. Homogeneous ordinary differential equation, ODE. So that's pretty helpful. Differential equation is analytic. So that is to say, if the coefficients are analytic, then f of x defined by this algebraic equation and also by the differential equation are analytic, or is analytic here, plural. We use the singular here, is analytic. This is a great fact. Okay, so it is not difficult to appreciate the importance of analytic function. In fact, most functions that you, in everyday usage of calculus, geometry, physics, are analytic functions. And not just for these elementary functions, and many more advanced examples would include quote-unquote special functions in various branches of mathematics, such as probability theory, mathematical physics, number theory. More advanced functions such as what we call the gamma function. Gamma function is arguably the most fundamental among all special functions, quote-unquote special functions. Gamma function, Bessel function, also known as cylinder functions or cylindrical functions, because they appear in physical problems with cylindrical symmetry. So if you study the theory of electromagnetic propagation in, say, this kind of what we call in fiber. Fiber. So these are often assumed to be cylindrical shaped. So you have a boundary condition imposed by the shape of the cylinder, and you study the wave equation, named Maxwell's equation. Inside those domains, Bessel's functions show up. Okay, so Bessel's function is characteristic of cylindrical symmetry in mathematical physics. So Bessel functions, elliptic functions. Elliptic function is the key ingredient. Elliptic functions and elliptic curves are the key ingredients that proved Fermat's last theorem. Recently, there is a video, 8-hour video on YouTube explaining that. So yeah, elliptic functions played a huge role in number theory and also applied mathematics such as mechanics. Some of the most simple problems in mechanics, like the pendulum. The pendulum requires elliptic functions to get the full solution, and also in rigid body mechanics. So elliptic functions were, without exaggeration, the crown jewel of 19th century mathematics. And complex analysis, among other things, were developed to study the properties of these special functions. And a great collection of the properties of these functions are in the book by Abramowitz, not Abramowitz and Stegan, but that's a table, but rather in the book called A Course in Modern Analysis by Whittaker and Watson. A course, even to this day, is a great reference for all these special functions. It's like a museum of classical special functions. A course on modern analysis, or course of modern analysis by Whittaker and Watson. In particular, Watson was a complex analyst, and Whittaker was an astronomer and mathematical physicist by Whittaker and Watson. Just a monumental work. Even to this day, this is still highly cited because of its extensive treatment on special functions, more advanced special functions. These are all examples of analytic functions when its domain is appropriately specified. You know, very cool stuff. So this explains why analytic functions play such a big role in mathematics and its applications. At the same time, it becomes clear why we can isolate the subject of analytic functions as a separate branch of mathematics. All right, so great deal, important stuff. All right, so now let's take a look at the second section of chapter 0, that is analytic function of a complex variable. Once again, this is an overview or motivation for the entire book. Okay. And let's be honest, people who are taking complex variables probably seen complex numbers earlier, at least from a manipulation point of view, right? It's like people who are taking real analysis must have seen real numbers before, right? So the point of complex variable, actually the course of complex variable do not assume that you've seen a definition of a complex numbers, okay? But it does assume that you've already seen how the algebra works, okay? So I think it's fair to drop the motivation here, okay, without defining it from the very beginning, because that's the job of chapter 1. This is still chapter 0. Okay, so already in studying the simple analytic function, the polynomial, right, it provides expedient. It proves expedient to consider it as a function of a complex variable. So the complex number arises even when you study the simplest kind of function, the simplest kind of analytic function, namely the polynomials. Right? When you want to solve for the roots of a polynomial, you don't always get a real root, right? So complex number was introduced there. Right? And actually in my video on complex numbers, it's called 300 Years of Demystifying Complex Numbers. Complex numbers was first introduced to solve cubic equation, not quadratic, okay, but cubic equation. Because over there, and in the video you will see there, is that the cubic formula, which was discovered in the Renaissance in Italy, the cubic formula, which is the counterpart of the quadratic formula for the quadratic equation, obviously. The cubic formula mysteriously sometimes requires complex numbers to get to real roots, even though the root is real. But if you apply the cubic formula to solve for it, in a process, you will encounter complex numbers. So which was a great paradox. So here it says, the text continues, says, indeed, only such approach, namely the introduction of a complex variable, only such approach reveals that this function takes on any value. This is a polynomial. Let me first take any value, for example, 0, for n values of x, some of which may coincide. That is to say, a polynomial f of x, just write it down, f of x equals x naught, a naught, right, a naught plus a1 of x. I know the reading was a little bit chaotic, sorry about that. I'll reread everything. Okay, this is the polynomial. Right. So even for polynomial, an assumed to be non-zero, even for polynomial, it proves expedient to consider it as a function of a complex variable. We need complex variables. It says, indeed, only such an approach reveals that this function takes on any value, for example, 0 for n values of x, some of which may coincide. That is to say, f of x can be factored in the form of an x minus x1 times all the way to x minus xn. So if you want to do that, you can't always do so in the set of reals. Such expansion or factorization, the factorization isn't always possible in reals, even though the coefficients are all real. If x is constrained to be real. Yeah, this is a great miracle, exactly. A bit of a miracle that a complex field is already algebraically closed. Exactly. That's the great beauty of complex, sorry, not complex, but fundamental theorem of algebra. Right? So if your coefficients are all real, you still need complex numbers. You need complex numbers to factor it completely into linear terms. However, if you change the coefficient to complex numbers, you don't need new numbers. Right? So this is the meaning of algebraic closeness, which is indeed a miracle. There's going to be so many miracles, man, in the course of complex variable theory. Things are just, that feels too good to be true. And one of which is the fact that local properties of analytic function often have global consequences. If it converges in a neighborhood, it converges on the whole domain, that kind of thing. Right? If you have one derivative, if the first order derivative exists, automatically you have infinitely many orders of derivative. The things that feels too good to be true are actually true in complex variable. Very, very surprising stuff. Okay, so naturally, in the text it says, naturally in studying polynomials as functions of a complex variable, we can assume that the coefficients to be arbitrary complex numbers. Okay, so these are, so we can take, so now we can consider a naught all the way to an as complex numbers. And it turns out that you don't need new numbers to solve for the roots if you consider coefficient to be complex. All right, so to do so, therefore we consider, as it turns out, okay, C is algebraically closed, miraculously. So the natural next step is to consider f of x as a power series of complex numbers. So next we consider f of x, f of z, and let's write f of z as the sum of an z minus z naught raised to the n from 0 to infinity. This is the natural next step. Right? And the series coefficients a naught, a1 all the way to an and keep going are complex, where the coefficients are all complex. Okay, now we have a definition for analytic function on for a complex variable. Definition: a function f of x is analytic on a set of points in a complex plane. Set of a complex plane, if in a neighborhood of every point of this domain, it can be represented by a power series. If I would reserve the word domain for something else, actually. In complex analysis, domain typically has a unique meaning, has a specialized meaning. Okay, it doesn't just mean the domain of the function, or the domain of a definition of a function. So I'm going to use the term set. Okay, if in a neighborhood, we'll define that in a second, of every point of this domain, of this set. Okay, every neighborhood of, in a neighborhood of every point of this set, it can be represented by a power series. Power series in z minus z naught, where z naught is that arbitrary point of any point, say z naught, of this set can be represented by power series. That is to say, f of z equals the infinite series. Okay, here we mean what we said earlier. When it comes to infinite series, it means that the infinite series, first of all, converges, and second, the sum of the infinite series, i.e. the limit of the partial sum, equals f of z. Okay, let's draw a picture. So this is a complex plane, real axes, imaginary axes, and this is a set, arbitrary set, all right, on which f is defined. Let's say f is analytic on this set, say S. F is analytic on this set S if for every point, z naught, here, this is an arbitrary point z naught, in its neighborhood of z naught. In its neighborhood of z naught, then, okay, this raises a little bit of a topological question. So can every point have such a neighborhood, right? So why don't we just restrict S to be open set? Okay, and let's just call it on an open set. On an open set. Okay, we'll define these notions again later, but here I just want to make sure this is the correct definition. Let's say S is an open set. This way, every point z naught has a neighborhood contained in S. Every point of S is an interior point. Then you can always construct this kind of neighborhood. So the definition of analyticity says, for every point z naught, there exists such a neighborhood on which this series expansion holds. So z is a point in the neighborhood. Z is a point in the neighborhood here. Let's say this is the center of the neighborhood, z naught, and z is an arbitrary point in the neighborhood. This is z. F of z on this neighborhood can be represented by this infinite series. Okay. This is the direct analog of the definition of the analytic function on the real line. You see, open set, arbitrary point inside the open set guarantees that the openness of A to B guarantees that there is a neighborhood of x naught. On that neighborhood, the infinite series converges to f of x. Here we're just doing it in 2D, basically. Okay? So that's the definition of analytic function on the complex plane. Okay, continue. So for this kind of function, we can extend the notion of calculus, the operations of calculus, to this kind of function. So we wish to, our goal is to discuss things like derivative integral of this function. So f prime of z, what will be define the properties, define and investigate the properties of derivatives integral of this function, the integral of f of z. And speaking of integral, one question immediately shows up, because the integral, well, it can be understood in two ways. Just like in regular calculus, right? You can use the integral sign to represent antiderivative, or you can use that with the appropriate endpoint to represent a definite integral. Right? So imagine, let's say, you understood the notion of derivative, then you can automatically understand the notion of antiderivative. It's just the inverse operation. However, what would be the analog of a definite integral in the complex sense? Think about it. Think about imagine putting yourself in the shoes of Cauchy himself, okay, when he was trying to erect this new theory on complex variable. How do we even approach the notion of an integral? Well, the thing is, on a real line, you can say the integral from a to b, because the real line is an ordered set. It has a total linear order on it. Integral of f of x dx. If you just transport this notion naively to the complex sense, let's say you have 2 points z0 and z1. Can you say the integral from z0 to z1 without extra modification? You cannot, because there are infinitely many ways to go from z0 to z1. Right? On the real line, if the interval endpoints are specified, the interval of, or the domain on which you integrate the function is now specified, but on the complex plane, because of the higher dimension, there's no canonical way to traverse from the point z0 to z1. So this notation in itself is problematic. So instead, you would have to specify the root, say L. Is a later we'll call this a contour. Okay, so this is what we'll call this a contour, and the contour, and this will be called a contour integral, which is the main object of study. Sometimes the contour integral is independent of the path and only depend on the initial and final point. This is very similar to the situation in vector calculus when you have a conservative vector field. Then the line integral would only depend on the initial and final point, just like, and its direct application is the conservative force, conservative vector field, conservative force field in mechanics. You can define things like potential energy. So in the bottom line is, in general, a contour integral, the integral in a complex plane needs to be defined over a curve or a piece of contour. You can't just simply state the endpoint, right? Because that's in general not well defined. Right? Because by specifying the endpoint, there's still ambiguity when it comes to traversing from one point to another. This is here. This is what we call, this notation, by the way, is called a contour integral. Very similar to the notion of line integral in vector calculus, but it is a unique object on its own. Because in vector calculus, when you do line integrals, you're integrating a vector field, and the outcome is a real number. You're integrating, you put in a vector field in there, and the outcome is a real number. There are two different kind of objects. Right? The input is a vector field, and the output is a number. Think of doing work in a force field. Right? The work is a scalar. But here, the contour integral takes a complex value function, returns another complex number. So really, you should think of this as the generalization of the integral from a to b on the real line, and not in terms of vector calculus. Okay, this is what we call a contour integral. So our goal is to define these objects and study their properties. And they have many, many surprising properties. So there you go. Let me just erase that. Okay. extra motivation. Now, what should be even the barrel's role in C? Yeah, by the way, Wendelin mentioned the barrel's rule, which really is the fundamental theorem of calculus, right? The so-called Newton-Leibniz formula, which is actually the correct name. It should be called Barrel's rule because it was Newton's teacher. Barrel was Newton's teacher in Cambridge. He discovered the inverse relationship between, at least he did so prior to Newton, okay? He did so prior to Newton on the inverse relationship between what we call the derivative and integral. Okay, there is a Barrel's rule in C that illustrates the inverse relation. There is. It is called an antiderivative theorem. It's called an antiderivative. Actually, let me just go quickly to Wendelin. This is a. I mean, I don't want to put that in the notes here because. But it's still a question worth answering. The analog for that, or you can call it the fundamental theorem of calculus on a complex plane, would be the following. Hang on a second. The existence of antiderivative has several equivalent conditions. Here, let me just. Antiderivative. Hang on. Yeah. There's a result. So I'll put it on the site because it's a great theorem. A theorem. Now, this is what's up ahead, by the way. Theorem. It says if a function f of z. Okay. Now we're considering a function of a complex variable. If function f of z is continuous. This term will all be defined later in a domain. And by the way, the word domain has a special meaning. It means open, non-empty, open connected set. If f of z is continuous in a domain, say D, TFAE, the following are equivalent. My favorite type of theorem ever. A, f of z has an antiderivative in big D. Has an antiderivative let's say big F of z in D. Now, you know what? Let's draw the picture. This is the open set D on the complex plane. This is a domain D, non-empty, open connected. It means, i.e., on D, f of z, little z is big F prime of z. And this holds true everywhere in the domain. This is part A. Part B. Part B says the integrals of f of z along any contour lying entirely in D and extending from any fixed point z1 to any fixed point z2 all have the same value. Okay, it's a very long sentence, but basically the picture is rather straightforward. Let's say if you have a fixed point z1 in D and z2 in D, and connect them with a path that lies entirely in D. Okay, so let's call this L. So let L, first of all, let z1, z2 be any point in D, and L be a contour lying entirely in D. Then the integral over L, integral along L, f of z dz, is simply f of z2 over z1. So this looks like the antiderivative rule, right? The fundamental theorem of calculus. I.e., this is independent of L. I.e., independent of L. And because of independence of L, in this specific situation, because of path independence, you can write the integral from z1 to z2. So this is actually well defined because you already know this is path independence. I loosely recall Goussat's theorem. Do not if know people. Yeah, Goussat's theorem is actually Goussat's theorem is a different matter. Goussat's theorem is a different matter, and actually that's the foundational results of counter integration theory. Actually, now once again, a very miraculous result. Goussat's theorem. Goussat's theorem says if a function is analytic, then it's roughly speaking, okay. If the function is analytic, then its counter integral along a closed curve is 0. Which is amazing, right? So, and it underlies many of the formulas that you will see, including things like Taylor series and whatever. In complex analysis, they all relies on that theorem, the Goussat theorem, that Wendelin just mentioned. So this is part B. Part B says if Z1 and Z2 are in D, and L is a contour lying entirely in D, then the counter integral of f of z dz is simply the value of f of z2 minus f of z1, and this is independent of the path. And for that reason, in this situation, you can write the integral as integral from z1 to z2. Whenever you have path independence, you can write that. Whenever it is not clear, you cannot. So C. That's part B. And part C says the integral of f of z along closed contour lying entirely in D all have values of 0. Closed contours. So now let's say you have a closed contour. Say this is D, all right? And in there's a closed contour. The notion of a closed contour simply says the starting point equals the ending point, okay? It may cross itself and do all this kind of query stuff, but as long as it returns to the original point, it's called a closed contour. So the third property says for the integrals, counter integrals of f along any closed contour lying entirely in D is 0. So there's that. And by the way, I'll give the reference for the theorem. This is Brown and Churchill, a Western classic. Brown and Churchill, very approachable, great exercises, and also approachable exercises. Great for self-learning. Okay, I can't praise this text enough. Brown and Churchill, page 141, theorem. 9th edition, by the way. This is a book with great number of editions. I think the book by Markushevich only has 2 editions. Anyway, doesn't matter. So this is a result that is a direct analog of the Barrow's rule in C, okay, or the fundamental theorem of calculus. Okay, so we will of course see this result, how it's proved and whatnot, and yeah, including Goussat's theorem. Okay. Anyway, so our goal, as I stated earlier, is to study the notion of derivative integrals for analytic functions. And another important goal is to characterize analytic function, right? So what are the conditions? What are the necessary and sufficient conditions for analyticity? That's also an important question. Okay. Characterizing analyticity. What are exactly analytic functions on the complex plane? Characterization of analyticity. And the answer to that is also extremely surprising. So for this to be true, you just need the function f to be first order differentiable, once differentiable in a neighborhood, which is ridiculously good. Think about this. In real variable theory, if a function is once differentiable, you can't even guarantee that it has two derivatives, let alone it has a power series expansion. But it turns out that in C, you just need one derivative in a neighborhood and everything just suddenly miraculously fall into place. Okay, this is another great thing about a local property, quote unquote, implies automatically leads to a global result. Okay. Anyway, I'm just dropping these as carrots, dangling the carrots in front of you guys, just to let you know how amazing this field really is about. Anyway, so let's see. In the course, we'll prove the following fundamental fact. Okay, we'll prove this is a fundamental fact, and we will write it down. In the course, we will prove the facts, which are of fundamental importance. Okay, for a function f of z, to be analytic inside a circle, say, to be analytic inside a circle in the complex plane, in the complex, say, z plane. Maybe I'm wrong. Continuity implies no. Continuity do not imply. Continuity is too weak. Continuity do not imply analyticity. Instead, once differentiability in a neighborhood implies analyticity. As continuity assumes a primitive and then holomorphic, hence analytic. Hold on a second. Is continuity enough? I don't think it's enough, because I can easily give counterexample. Let's say f of z. By the way, I mean, we're jumping ahead. F of z equals z bar. This is not analytic, but it's continuous. But z bar has no antiderivative. You see, Wendelin, your argument is not correct, right? So you see, z bar has no antiderivative. Yeah, z bar just does not have antiderivative. You cannot get a function. But anyway, yeah, the reason why you cannot have a function whose derivative is z bar in a complex plane is dictated by the so-called Cauchy-Riemann equation. The Cauchy-Riemann condition. Let's say suppose it has an antiderivative, then the antiderivative must satisfy the so-called Cauchy-Riemann condition, and z bar would fail that condition. So yeah, this function is continuous, but is not analytic. Continuity is too weak, but once differentiability, surprisingly, is enough. Okay. All right. So once again, these will be proved. For a function f of z to be analytic inside a circle in the complex z plane, it is necessary and sufficient. Yeah, it's probably messing things up. Yeah, Now it is necessary and sufficient that the following four condition holds true. We need a fourth condition holds true. So it's an if and only if statement, necessary and sufficient, or that the following four conditions holds true. Okay, so one, it says the function f of z has a derivative at each point inside the circle. So f prime of z exists everywhere inside the circle. Is it four conditions hold true simultaneously? Is it that the following? Huh. Anyway, so this is one. Let me just finish writing everything and I'll discuss this. So I see a progression. It was first it was Russian for mathematicians, then now it's math Russian style. See a progression. Glad you see you're using Russian books. Exactly, I'm using Russian books. So guys, feel free to go to the Internet Archive and check the book for yourself. Right now we're on page 13. So the second condition says if we write f of z to be u of x and y plus I times v of x and y, you have u and v to be twice differentiable functions. So u, v are in the set C2, are in the class C2. C2 means their second order partial derivatives all exist and are continuous. And then it satisfies, and uv satisfies the Laplace equation. Laplace PDE, okay, Laplace equation. uv satisfies. So this is a great connection between complex analysis and PDE. Satisfy the Laplace equation. And this is why complex analysis were traditionally the dominant technique in fluid mechanics. Because under a certain ideal situation, fluid flow can be modeled by Laplace equation. And nowadays, well, due to the advent of more advanced numerical methods, that approximation has become less essential, but still it provides at least the basic physical intuition. So great usage of complex analysis in fluid mechanics. So it seems like if you want to analyze the airflow around the wing of an aircraft, traditionally you use a lot of complex analysis. But nowadays you have more accurate modeling and whatnot. But still, a first approximation given by complex variable theory is still valuable. The uv satisfy the Laplace equation and are coupled through the following equation. And this is a Laplace equation and what we call the Cauchy-Riemann equation. So these conditions aren't completely, say, minimal. Okay, some of them there's implication within it. For example, if you assume, actually we'll see in a second, if you assume Cauchy-Riemann, then the Laplace equation then follows. It's actually just a simple exercise in calculus. We'll see that in a bit. Let me just finish writing it down and we'll prove it in a second. So Cauchy-Riemann equation says du over dx equals dv over dy, and du over dy equals minus dv over dx. So this is Cauchy-Riemann equation, and actually it implies a Laplace equation. Let's see that how it works. So you can use the fact that UVs are in C2. This way, the mixed partial derivatives are the same. So this tells us that d squared u over d x dy is the same as d squared u over dy dx. That's the result in multivariable calculus. If the second order partial derivatives are all continuous and the mixed partial derivatives are the same. I believe it's called the Claret theorem. Okay, but anyway, this tells us the partial differentiation operator commutes basically. So you can actually show Cauchy-Riemann. Sorry, not show Cauchy-Riemann, but show Laplace, assuming Cauchy-Riemann. So U and V are coupled in this system of PDE. So assuming the Cauchy-Riemann equations hold, then you can derive the Laplace equation. So let's do that real quick. So d over, so first you have du over dx equals dv over dy. And then you just do d over dx on both sides. This way you get d squared u over dx squared equals d squared v over dx dy. Okay, and the second Cauchy-Riemann equation says du over dy equals minus dv dx. So you're gonna d over dy on both sides, and you get d squared u over dy squared equals minus d squared v over dy dx. But you see, because of the equality of mixed partial derivative, adding the two equations, you just get d squared u over dx squared plus d squared u over dy squared equals 0. Okay, yeah, there you go. So therefore, the Cauchy-Riemann equations imply the Laplace equation. And Cauchy-Riemann equation, as we shall see, it has an important geometric intuition as well. Actually, let me just show that like right away, why this is useful geometrically. So a little bit of a jumping ahead. We know that complex multiplication is a scaled rotation. So you haven't seen that. I made a video about it. Not dedicated to complex multiplication, but just non-complex numbers in general. I think that's my latest video actually. It was 3 weeks ago. I should publish more videos. So the video in which we discussed the notion of complex multiplication. Let's just derive that real quick. So assuming you have this symbol I, okay, so assuming that this symbol I that allows you to do arithmetic with a plus ib in the usual way, except one extra rule, that is I squared equals minus 1. So you get AC minus BD, plus I AD plus BC. Okay, just a regular expansion using the rule that I squared equals minus 1. We explain this rule later in the series, but now we're just going to use this as a convenient rule. You can even treat this as a mathematical fiction if you want to, but later on we will show this actually exists. Okay, so of course I is not a real number, but this is still a valid mathematical object. So this is a rule of complex multiplication. But if we treat complex numbers as points on the plane, you can write, say this is AB, this is the ordered pair AB, A plus IB. You can describe the same vector using its length and its angle it makes with the positive real axis. So let's say the length is r1, okay, and the angle is theta 1. You can easily convert a and b from r and theta, provided a and b are not 0 simultaneously. So you're going to just write Okay, A equals R1 times cosine of theta 1. It's just a conversion between Cartesian and polar coordinates, nothing else. And B equals R1. Okay, B equals R1. B equals, sorry, R2, R1, yeah, R1 sine of theta 1. And C is R2 cosine of theta 2. And D is R2 sine of theta 2. Right? And if you just plug in these values into the multiplication formula, you get this. R1 cosine of theta 1 plus I sine of theta 1 times R2 cosine of theta 2 plus I sine of theta 2. And on the right, you have R1 times R2. The real part, AC minus BD, would just be cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. Okay, and then plus I of AD BC. AD would be R1, R2, still have that factor at the front. AD would be cosine theta. It's cosine theta 1, sine of theta 2, and then plus sine of theta 1 times cosine of theta 2. But as we all know from trigonometry, the right-hand side is exactly the additional formula for cosine and sine. So it's R1, R2 cosine of theta 1 plus theta 2, and then plus I times R1, R2 sine of theta 1 plus theta 2. So what does it says? It says complex multiplication is scaled rotation. You're just going to add theta 1 and theta 2. So the angle is added, and the length is scaled. So the new length is R1 times R2. The result of a complex multiplication is a new complex number whose length is the product of the original two complex numbers, and the angle, the new angle, is the sum of the angle. This is one of the miraculous results. The elementary but still miraculous result in complex variables. So complex multiplication is just scaled rotation. It gives us an extremely efficient way to encode rotation. I discussed this in the 3D rotation stream because in linear algebra, to describe rotation, you need a 2x2 matrix. However, the 2x2 matrix don't have 4 free variables. It has to be an orthogonal matrix, so it introduces extra constraint. And for that reason, you actually have one free variable to describe rotation. And complex number achieves that effortlessly. You just need the angle and the rotation calculation. The coordinates of the rotated vector is encoded in complex multiplication. So let me just draw out the result. Okay, this is a new vector, a new complex number, C plus ID. R1, R2, R2, theta 2, R2, theta 2. Okay, the length is R2, angle is theta 2, and the new angle, okay, this new angle here, is theta 1 plus theta 2, and the new length is R1 times R2. So that's pretty neat, right? That's pretty neat. So we can consider this fact and write it in the following way. So now if we fix, say, z0, fix z0 to be a complex number at non-zero. Fix z0 to be a complex number in z0, fix z0 to be a complex number in C, which is non-zero. Then the function, which is the simplest function possible in the complex plane, the linear function, z0 times z, the linear function, can be seen as a geometric transformation. Can be seen as a transformation, so it works like this. The function f from c to c, let's call it w equals f of z, okay? F from c to c. This is a transformation is the scale rotation transformation. Is a transformation that scales is the scales using the length of z naught and rotate according to the angle of z naught. That does scaling according to z naught absolute value. Oh, by the way, this is the length, the notation of the length, and rotate according to the angle of z naught. A is denoted as argument, arg z naught. Okay. So this is a picture here. So usually in the complex analysis, we visualize the complex function using the two-plane method. Of course, there are different ways. This is a very common way. You can treat the complex function as a transformation. It transforms the complex number into another complex number. So you need two copies of the complex plane because you cannot draw a four-dimensional space. Not easily so, anyway. So this is a z-plane, and the function maps from the z-plane to the w-plane. So what is the action of the function f? So this is a w-plane. Say this is an arbitrary vector c. As we said, it's just a scaled rotation. Okay, so this is the original vector. What is w? W is scaled of z. The length is scaled of z. W is f of z. The new length is z length times z naught length, right? And the angle is added by the argument of z naught. This is the scale rotation. So as long as z naught is constant, the rotation angle is fixed. Remember, the rotation angle, this is a fixed number because x naught, z naught is fixed, so the rotation angle is fixed. Although the scaling factor z naught length is fixed, that's not so important what we're about to see. But this is fixed. The angle is fixed is crucial. The angle is fixed is crucial. Actually, if we go back to say f prime of z exists everywhere inside the circle, what would that mean? What would that mean? Well, it would mean following. So if let's say f prime exists in a little circle, in a circle that is near in a circle, sorry, if f prime of say f prime, my God, I'm struggling for a word here. So let's say f of let xi be a fixed number in C. This is xi. Or actually zeta. I should use zeta probably. Zeta would be the Greek counterpart of z. Okay, so this is the z plane. On the z plane, there is a point called zeta. Is that how you write this? Zeta. Anyway, screw it. Just write the xi. Okay. Anyway, so this is the point, and you have a circle. Imagine you have a little circle centered at zeta, on which the function f is defined. Okay. We always wanted a neighborhood of the point in complex analysis. So imagine f is defined in this neighborhood. And we say that f prime of zeta exists. Exist means the derivative is defined as follows. The limit of z goes to zeta as f of z minus f of zeta divided by z over zeta. This limit exists. This limit exists. So, and when it exists, it's just called f prime of zeta. Anyway, so let me just actually just bring this together. Suppose f prime of z, which is defined as this limit, exists. Suppose this is true. Let's think about what this expression has to offer. Because now, if let's say z is just a real variable and zeta is a real variable. In calculus, we say the limit exists if the two-sided limit exists. Right? If you approach z, imagine now they're real. Okay, if they're real, then it means when z approaches zeta from the right, the limit exists, and if z approaches zeta from the left, the limit also exists, and they're the same. If all three things happens to be true, then we say the limit exists. But here, because we are working in a higher dimensional space, there's no canonical direction of how to approach z, how to approach zeta. So that means if the limit exists, then it must mean that regardless how you approach z, okay, any arbitrary direction, the limit exists and is the same number. So even though this looks like a rather arbitrary, not arbitrary, but innocent looking assumption, right? You just want this limit to exist. But because you're working in a two-dimensional plane, the limit has to exist and the same for all possible ways that z approaches zeta. So let's use our intuition in calculus. This just means that when z is close to z naught, i.e. when z is close to z naught, imagine here, this is a point z, gets very close to z to zeta. If z is close to zeta, you have an approximation. That is to say, the difference quotient, the finite difference quotient, is approximately a fixed number. Remember, now you assume this exists, okay, that's a fixed complex number. Say L. Say L. This just means that when z is close to zeta, this finite difference quotient is approximately L. Let's think about what this means geometrically. This is approximately L, i.e., under the same assumption when z is close, blah, 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 f of z minus f of zeta is approximately just L times z minus zeta. But what does this do? This is just multiplying by a complex number. It's a fixed complex number. And what does multiplying a complex number do? It's a scale rotation. So this is the z-plane. Okay, let's look at the situation on the w-plane. This is the w-plane, the plane where the values live, the values of the function live. All right, so this is w, and imagine this is a point of f of z, f of zeta. Okay, f of zeta. So you were saying that this is our vector z minus zeta. How do you draw f of z? Well, f of z minus f of zeta is just approximate rotation. Okay, so let me just import the same vector z over z minus zeta here as this vector. Okay, this vector is z minus zeta. Here, this equation just says the difference or the increment in f is approximately a rotation of the increment in the scale rotation of the increment in the independent variables. So you're just going to rotate this and get a new vector. This is the position of f of z. So this new vector, this new green vector, is nothing but a scale rotation of the old increment vector z minus zeta. So I'm going to label this. The angle here is the argument of L, and the scaling factor scaling factor, I mean, it's not super important, but yeah, I was saying the angle is what matters. The angle is fixed, given by this L. If the limit exists and L is a fixed number, so the angle is fixed. And the scaling factor is, of course, scaled by the length of L, the absolute value of L. Okay, so this has consequences. This has consequences. So imagine if you have two curves intersecting in a z-plane. Let's say you have two arbitrary curves intersecting in the z-plane, and the curves have tangent vectors and intersecting at the z-plane through the point zeta, and the tangent vectors are all rotated by the same angle. So the tangent vectors are all rotated by the same angle. The length may change, right? The length of the tangent vector may, well, first of all, they may be scaled, but scaled by the same amount. The important part is the angle between the new tangent vectors and the old tangent vectors are the same because of the, well, rotation business. So what this says is, if a function is differentiable, and if you see that as a transformation, it is a conformal transformation. Conformal transformation means angle preserving. And this is hugely important in navigation. Well, historically so, before the age of satellite and all of that. So because of the geometry of complex rotation, a differentiable function corresponds to a conformal mapping. And this is hugely useful. I just gave an example in cartography. In cartography, well, historically, it is important to create charts that has this conformal property. And in fact, the most popular, even to this day, the most popular map is based on so-called Mercator projection. A great topic for a video or a stream explaining the Mercator projection. Hi, good morning. Здравствуйте. TEP has been helping with my Russian a lot. So it's very early in Moscow time, I believe. So yeah, this is a Mercator projection. The Mercator projection, of course, is the most popular map in the world. Well, at least in the Western world. I'm not sure in other parts of the world. It's because it's actually quite interesting. African countries do not like this map at all. No, some countries actually ban this. How crazy is that? Well, why was this map originally invented? So imagine if you connect, say, 2 points on the map from London to New York City. And you can measure the angle it makes with these vertical lines. Of course, these vertical lines correspond to the line of constant, is that latitude or longitude? Constant longitude. So these lines correspond to constant longitude. And the Mercator map is designed in such a way that it is conformal. So if you, let's say, connect, say, London and New York, the line on the map, right, the straight line on the map that connects to the straight line on the map, I mean, that is the one connecting New York and London, or whichever 2 points, and regardless of distance, actually, it doesn't have to be close. The angle between the line and the vertical lines, namely the lines of constant longitude, will be the same as the actual path. Will be the actual path of the trajectory and the lines, or should be say the great circles of constant longitude on the Earth. So this is hugely convenient because back in the days, you only have a compass for navigation. Okay, if you draw a line on the map, you can actually sail along that line. And to locate that path, you simply need to measure the angle between the drawn line on the map and the vertical line. So this is a great invention for the age of sail. So and that's the example, perhaps the most famous example of conformal mapping. But conformal mapping isn't just used for Mercator projection, but map projection in general. Of course, not all maps are conformal, but a lot of maps were based on that principle. Conformal map, and cartography on its own is a hugely interesting topic. A lot of mathematicians, including Euler and Lambert, worked on the field. So I believe actually this complex analysis was first realized to be important in the field of cartography. A differentiable function in complex analysis corresponds to a conformal map. Okay, it is useful in cartography, and later on turns out to be useful in solving a Laplace equation. You can transform a complicated domain conformally into a simpler domain. And the nice thing about conformal map is that if the original function satisfies the Laplace equation in a complicated domain, the transformed version under the conformal map still satisfies the Laplace equation. So the idea is you can transform a complicated domain into a relatively simple one, and then solve the Laplace equation on the simple domain and transform the solution back to the original domain. So that's the idea of here in the text. I think it covers it, called the conformal mapping technique for solving PDE, and in particular, a special example for that would be the Schwarz-Christoffel transformation. It should be in the text. Schwarz-Christoffel transformation. So that's the Riemann mapping theorem guarantees the existence of a conformal map, and the Schwarz-Christoffel transformation tells you how to construct it. Okay. So that's a great application of complex variables. So here I was saying, we were just listing these conditions here for a function to be analytic. I think here in the text it says the following 4 conditions hold true. I haven't written down all the conditions yet, but I think you just need one of them to be true, and the rest are immediately true. I think that's what it means based on my prior exposure to the subject. Because f prime exists everywhere in the circle certainly already implies this. And 2 also implies 1. So I think, starting from here, for a function f of z to be analytic inside a circle in the complex z plane, it is necessary and sufficient that the following condition holds true. I think this is actually equivalent. But the text, this is the original phrasing of the textbook. So I'm a little bit unsure why it is phrased this way. But let's continue. So once again, this is just an overview, not meant to be fully rigorous. Okay, rigor will come later, including this little discussion on conformal map. Okay, the intuition of it. Okay, it's just right now we're giving away these insights of complex analysis without being too technical. The third condition says the function f of z is continuous. All right, and f of z is continuous inside the circle. Oh, I forgot to mention, why do African nations hate the map, hate the Mercator's map? Because it has this property of area distortion. So African nations actually argue that, jumping from mathematical definitions and theorems to politics, the Mercator projection, I can't help but mention this. The Mercator projection was rejected by a number of African nations due to its distortion of size. It preserves angle, but it distorts area. For example, Greenland is actually much, much smaller on the map, and Africa is much, much larger. And the African nations believe that due to the proliferation of Mercator's map, of Mercator's projection-based maps, people perceive Africa as less important as it actually is, because you see, oh, it's just a small area, and it causes the continent to lose economic opportunities. And also Mercator's projection, the map based on Mercator's projection, was essential for the age of sail, and which led to the enslavement of African populations, that sort of thing. So it has this colonial baggage associated with this particular mathematical tool. And even though Mercator himself did not develop the map of diminishing Africa, but unfortunately there are unintended consequences. Right? So the map was invented due to human priority, right? The navigation, the need for navigation. So the conformality, the angle, the preservation angle was prioritized, okay? And it has this mathematical property of size distortion. Here you can see how the real size is compared to the actual what's shown on the maps. So you see, on the map it feels like Russia is bigger than Africa, whereas in reality it's totally untrue. Right? Africa appears to be the rough same size as South Africa, but in reality Africa is over 1.5 times as large, you see. So African nations do not like this at all. Because of the great land distortion, critics like blah 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 considered projection unsuitable for general world maps. It has been conjectured to have influenced people's view of the world, because it shows countries near the equator too small compared to those Europe and North America. And has been supposed to have caused people to consider those countries as less important. So yeah, so for that reason, the African Union supposed a campaign of favoring equal Earth projection. So this is the area preservation map. And of course, each map projection has its own trade-off. If it preserves area, then it no longer preserves angle, which nowadays arguably is not such big of a deal because navigation already no longer relies on all compasses. But it's such an interesting piece of math history. See, this is the equal area projection. And the mathematics actually is much more complicated. You see, the area preservation formula is this, whereas the Mercator projection is a lot easier. Well, it's a lot shorter, actually. The derivation is also very clean. Perhaps we should show this in a different episode, in a different session. Yeah, you just need some basic vector geometry and calculus to derive that. Here, yeah, this is a projection formula for the Mercator's projection, and the derivation for Mercator's projection involves the integration of secant. The integration of secant is a great question of trickery in elementary calculus. It stems from this particular application, this integration of secant, and came from the need of calculating Mercator projection. It turns out to be the natural log, but Mercator did this essentially numerically, because back in his days there was, well, no Newton-Leibniz formula. Actually, back in those days there's not even natural log. So he essentially created the table of this integral using, well, numerical integration. So yeah, it was a great problem. Calculating this integral exactly was a great problem in the 17th century. And nowadays, first-year calculus student can solve that. One day you should become a geographer. Oh, hi, Andre. I don't know about me becoming a geographer, but I'm always fascinated by maps and history and stuff like that. So, the lesson here is that Mercator projection is a conformal mapping, And conformal mapping are naturally described by complex variables. All right, so let's continue writing the big theorem here. What's up ahead? Okay, where we're going. Condition 3. The function f of z is continuous inside the circle, and the integral of this function evaluated along every closed curve inside the circle is 0. Okay. So this is actually, yeah, this is not. I mean, let me write it down. And the integral, the contour integral, okay, contour integral. To be completely clear, this does not mean antiderivative. Okay, the contour integral of f along every closed curve, closed contour. Let's use closed contour. Closed contour, once again, means the endpoints are the same. Okay? The starting point and the end point is the same. The closed contour inside the circle is 0. And it has to be every closed contour is inside the closed contour inside the circle is 0. So that's a great characterization of analytic function. And the last one, part 4, actually, I didn't know this one. This one is new to me. It says, inside any concentric circle of a smaller radius, the function f of z can be approximated by polynomials with an arbitrarily high accuracy. This is such a, you see, this is very unusual. I mean, at least I didn't know this. Okay, so let me just draw a picture. So if you have, say, okay, so this you have a circle on the complex plane in the okay, this is a circle, and now it says inside any concentric circle. So imagine you have a concentric circle, but with a smaller radius, like this. Inside any concentric circle with smaller radius, the function f of z can be approximated by a polynomial with arbitrary high accuracy. Oh, I guess that's why. Because you have a power series expansion. Right? Because you have a power series expansion, the series expansion equals f of z. Right? And then you can say, I want a finite truncation of the series so that the error is less than a particular threshold. And this can be done because the convergence is uniform. This is something that will be defined later. Basically, uniform convergence controls the errors in the worst case scenario. Okay, so this is also a great characterization. So it's inside any concentric circle, as is shown here. You can approximate f of z by polynomials, and you can do so with arbitrary degree of accuracy. Concentric circle of a smaller radius. We don't guarantee this is possible for the entire radius, but on the smaller radius, because on the entire radius, on the whole radius, okay, the convergence may not be uniform. Inside, however, the convergence is uniform. As long as the radius is a little bit smaller than the actual radius of convergence. As long as that's true, then the convergence is uniform, namely you can control the worst case error. Okay, that's the intuition here. The smaller radius, the function f of z. Guys, you know what? This is a just an observation. I don't know why, but it is very surprisingly. I'm very surprised by this and pleasantly surprised by this. The viewership, the concurrent viewership is extremely stable. For this one compared to my other sessions, it's been just like on average 20 people constantly. plus or minus epsilon, but I was very surprised by this. By polynomials with an arbitrarily high accuracy. So these are all big results, massive results, and they once again, in some cases, highly non-intuitive. Because how come the first order derivative implies the existence of derivative of all order and the existence of power series expansion? This just sounds too good to be true, but it is actually true in the complex field. How do you go about choosing your study material? How do you go about, well, I like, how do I say this? I like books that are thorough. I like book. First of all, I prefer, in that hierarchy, okay, I prefer books over notes and notes over slides. I mean, just a general ordering. Because I find books to be less likely to contain typos and generally have bigger viewership. Not viewership, I mean, I'm doing too much YouTube. There's readership, okay? And sometimes it's just purely based on my experience, because when I was a student, I don't have knowledge about how to choose certain textbook and whatnot. During that time, there was no AI and other things, right? You usually do this through the words of mouth from professors and whatnot. Sometimes the textbook are assigned to you. You have no choice. But typically, that's how, I mean, I don't have a systematic method for selection. Sometimes it's just you choose one and you stick to it. I don't spend an awful lot of time thinking about what study material I use, right? Instead, I'll just try to get some opinion from others, hopefully from people who with actual experience in the subject, and I'll get their opinion and I'll just follow their advice. It's pretty simple. And after I get enough experience, I will form my own opinion. So, sir, can you also explain counter integration with branch cut? Yeah, this is part of the course. You of course do counter integration with branch cut, but not today. Today is just an overview. Okay, we will see, of course, examples of counter integration with branch cut. These are important. These are important examples, and they have great applications when it comes to evaluating tricky integrals and whatnot. Actually, guys, I started from. Actually, when did I start? Actually, I started from 7, didn't I? 7, didn't I? So it's getting close to 4 hours. We'll do another half hour, and we will end the stream. Okay. So, anyway, the final concluding remark of chapter 0 in Markushevich says, these propositions, these ones, 1, 2, 3, 4, these propositions, this is a big result. Let me just actually perhaps box that. These results are the great reward of complex variables, among others. So these are more like qualitative results. They're more like qualitative results. However, we'll see also formulas and you can use with actual calculations. But these are the fundamental principles, so to say. These propositions form the basis of the theory of analytic functions of a complex variable. Each of the properties A to D can be used to define an analytic function of a complex variable. Each of these properties can be used to define an analytic function. In this course, we will use the definition based on property A. So actually, we will use this as a definition. You must be like, whoa, what are you doing? You already defined the analytic function as an expansion of power series. How come you can just switch definition halfway, don't worry, they turn out to be equivalent, which is highly non-trivial. It's highly non-trivial. It turns out that the existence of a first-order derivative inside a circle would imply the existence of a power series expansion. But we will prove this as a theorem. Okay, this is proved as a theorem. It's just that historically, analyticity was initially defined as the existence of a power series expansion. This definition here is historically accurate. But the great surprise of the complex number theory is that f prime exists everywhere inside the circle is actually equivalent to the existence of power series expansion. Okay, from an exposition point of view, from a position of pedagogy, it's easier to build the theory from assuming f prime exists, defining f prime, and then prove that this power series exists. It's just easier pedagogically speaking. And there's no mathematical difference here, okay, because it all turns out to be equivalent. Okay, it's a great result. It's a counterintuitive result. But we're going to do this sort of in this way, because that's usually how a complex analysis book is written. It doesn't matter if you use a Russian text or some other text. Okay, this is just usually how complex theory is presented. Complex number theory is a very mature field. Anyway, so let's continue here. In this course, we will use the definition based on the first property, and only subsequently we'll show that this definition is equivalent to that in terms of power series, okay, as we just said. In many applications of analytic function in physics and mechanics are based on the second definition. That is the Laplace equation and the Cauchy-Riemann equation, understandably, because Laplace equation is hugely important in physics, in electromagnetic theory, heat transfer, that kind of stuff. Also probability. Laplace equation is also extremely important in the theory of probability, and in particular stochastic process, Brownian motion. Laplace equation shows up in Brownian motion. Well, it is hardly surprising because Brownian motion is connected to heat equation. I was just saying heat transfer, heat equation was connected to Laplace equation. So same mathematics, different manifestation in the physical world. Okay, and also fluid stuff. Fluid mechanics also traditionally relies heavily on Laplace equation. Anyway, for instance, the so-called planar problem of thermal and electrical equilibrium and the problem of laminar flow of fluid around flat profile lead to the Laplace equation, from which the various solutions or analytic functions can be built. Okay, so that's the motivation, okay, which is a lot. This is the complex analysis was the crown jewel of 19th century mathematics. And virtually all the great names that we know from calculus and analysis worked on them. Gauss, Riemann, Cauchy, well, it's already there, Laplace, and who else? Weierstrass, yeah. They contributed to the theory. Okay. Anyway, so with this out of the way, let's do some complex numbers from the beginning. Okay. So anyway, complex numbers and their geometric interpretation. That's the first chapter. You kind of already see what's going, right? So we shall do this part of the book rather quickly. Complex numbers. So this is like pre-calculus for complex analysis. Complex numbers and their geometric interpretation due to Gauss. Complex plane and the geometric meaning of complex multiplication was discovered by Gauss. I believe in West Germany, former West Germany, there was a post stamp that commemorates the Gauss's contribution to, well, Gauss's It's like bicentennial birthday. Let me just and with a so West Germany in celebration of Gauss's bicentennial birthday have a set of stamps. Okay, Gauss. Let me just search that real quick. Gauss stamp, post stamp. It's 1977 or something like that. West Germany. Yeah, this one right here. West Germany, 1977. No, this one. So Gauss was born in 1777, and this is the complex plane shown up in the West German post stamp. And actually, this one's not related to complex plane, but this is a post stamp by East Germany. I'm not sure this was also put out in 1977, but as you can see, something do unify enemies of different ideologies. Mass is such a great unifying force. Oh no, anyway, so the theory of complex numbers is usually presented in algebra. So here we recall the main definitions and results from this theory and arguments and augment them somewhat in our future exposition. Okay, should we do that? Andrei, actually, I'm getting a little bit tired, actually. Should we just spend the rest of the stream just chatting with you guys and do the actual math later? Are you guys tired? Because I'm a little bit tired today. Okay, so perhaps we will do this another time. Okay. Chapter 1. This is pre-calc stuff for the complex variables. We'll do this another time because I'm getting a little bit tired, and we will do that next time. Even though we just only give motivation, but still we discussed serious mathematics. You do conformal, yeah, absolutely. How can you do a complex variable course without conformal mapping? That's one of the most important aspect of complex number theory, complex variable theory. I mean, we gave an intuitive explanation of why complex variables is connected to conformal maps, but for sure we will do conformal mapping applications. Use conformal maps to solve PDEs, to solve the Laplace equation, that sort of thing. We'll do that. And actually, you know, the complex variables can be approached from different angles. It can be argued that you can make a separate course on complex variables conformal mapping theory alone, without using counter integration and all of that. You don't. It can be seen as a largely independent branch of complex variables. The study of conformal mapping can be seen as, first of all, its own unique branch. It's basically the special kind of transformation, right? So it's highly geometric. And on the other side of the coin, you can approach complex variables from an analysis point of view, power series, integrals, that kind of stuff. So this is why complex variables is a nexus of various branches of mathematics: geometry, analysis, right, topology, mathematical physics, algebra. So, yeah, in our first semester of complex, we had a test with two sort of problems to find a conformal mapping of area or another. Yeah, so indeed, this is, and often, I'm not sure about Markushevich's book, but at the end of Brown and Churchill, which is, I highly recommend as a kind of a backup, because let's be honest, Markushevich's text is not easy, but if you, let's say, run into trouble and you can't understand and you want more examples or something, still, Brown and Churchill is highly recommended. And in the appendix of Brown and Churchill, there's a table of common conformal mappings. So I think it's helpful for those kind of questions, because coming up original conformal mapping is not easy. You need a lot of examples to in the back of your head, so to say, to do these type of questions. Anyway, here, because I think I'm just gonna chat with you guys for the rest of the stream. I think I earned it. Okay, apologize if you still want to do more math. We'll continue for sure. So Andre asks, I recently seen that you're going to make a stream of PDE. I wonder which book are you recommending for beginners and PDE, what you're using by yourself? Good question. Actually, for the stream itself, I'm going to use my own notes from university. I don't have an online version for it yet, but it's still mostly standard material, but I like the presentation of it, so I'm just going to use it for the stream. However, excellent resources on PDEs exist, and there's a lot. So based on my experience, I would like to make the following recommendations. Okay. So once again, we're trying to promote appreciation of Russian mathematics. So I'm going to give some sources from Russian origin. Yeah, it's a good one. Fundamentals complex analysis by, yes, it's a good one. Yes, Saf and Snyder is great. Saf and, oops, that's my video game. Word of Warship. Okay, anyway, so that's just, anyway, let's continue. I was saying that here you have a source. What is the source called? What's the name of it? It's called Applied Partial Differential Equation by Richard Haberman. This is one. This is the one that is closer to my own notes, actually. So perhaps by Richard Haberman. There's so many great work on PDE. It almost gives you selection paralysis. So this one, unfortunately, it caused an arm and a leg. So this is the one. Applied PDE with Fourier series and boundary value problems by Richard Haberman. Okay, very, very approachable text. It only assumes multivariable calculus and ordinary differential equation, just basics of ordinary differential equation. Okay, you don't need extensive background in ordinary differential equations, but you got to know, say, what's the differential equation for a harmonic oscillator, that kind of stuff. This one is awesome. I like it. I like it a lot, actually. So if you're a complete beginner, I strongly recommend this one. And actually, if you're a complete beginner, I actually have another piece of advice, unsolicited, I'm sorry. Stop looking for the most comprehensive book on PDE. Okay, stop looking for the most comprehensive. It's just such an impossible task. The field of PDE is so large. Let's say you want PDE different, I mean, you may have different goals. So let's say if your motivation for study PDE is for physics, then this one is great. This one is great. It mostly covers PDE that arises in mathematical physics, heat transfer, wave equation, Laplace transform, Laplace equation, and all kinds of transform method, Fourier transform, greatly useful for physicists. However, PDE arises from different fields. Let's say if you want to study PDE for finance, then, well, unfortunately, this book don't have coverage over the Black-Scholes equation. Although the coverage on heat equation and Fourier transform is still useful. My point is, stop looking for the most comprehensive PDE book that contains everything. It's just impossible. And perhaps you're interested in numerical methods of PDE. Let's say if you're interested in numerical PDE, then you don't actually need extensive background in analytic solutions. You might need just a separate text on numerical PDEs. Okay. So it's I would say it's difficult to make recommendations because it really depends on what your background is and what you want to get out of the study. But this is a general purpose. This is general purpose. I don't claim this is comprehensive, but pretty comprehensive when it comes to typical introductory courses. There's even a guy on YouTube doing the series on Haberman, so go check him out. Only 637 views. Wow, that's criminal. Yeah, so this one, Applied Partial Differential Equation by Richard Haberman, is excellent. Go ahead, check out this one. And there's a more advanced version. So if you study this one, okay, study this or most of this one, or decide you like PDE, and the next natural progression would be Evans. Yes, Evans. We did a live stream on Evans's what's Evans's website? LC Evans from UCLA. Hang on, LC Evans website. Yeah, he is known for this book. He is famous because of this book, LC Evans's book on PDE. We did a live session on Introduction to Mathematical Optimal Control Theory, but there's some wrap-up to be done. So we'll come back to this at a future time. At least we want to showcase the full application of at least one example of the maximum principle. Okay, anyway, Pontryagin's maximum principle, I want to showcase that. But this is the same person. This is the same person. L.C. Evans, his book on PDE is very well known. Once again, yes, actually, I'm sure whether it is translated. I was about to mention that, man, Tep. I was about to mention that by Tikhonov and Samarsky. My God, that's such a great book. Anyway, so I was going through this order, okay, Western text first, and I'll pivot to the Russian one. Do you have shape theory and dynamical system? Not so much with shape theory, but dynamical system, yes. Like qualitative theory of differential equation. By that you mean I think you mean that, the kind of thing, or perhaps also fractals and chaos. Actually, yeah, I have experience in those, but not so much with shape theory. So yeah, this is Evans, the PDE. What's the name? Yeah, just the partial differential equation by Evans. This one, partial PDE by Evans. L.C. Evans. So this is another great book, but this is graduate level. And once again, as I was saying, it is impossible to have a comprehensive text. I mean, L.C. Evans himself admitted in the preface. If you want, let's say, if you're an ambitious beginner and you want to jump straight into Evans, I would advise do so with caution, because this one does not discuss the modeling aspect of PDE. It just gives you the PDE and then discuss its properties. There's not a whole lot of physical intuition involved. Okay. Instead, it tries to treat a PDE from the most general setup. Okay. There's not a lot of physical example, physical argument, and it's very, of course, due to its graduate nature, it's very proofy. I mean, this book is meant to bring the reader to the frontier of PDE research. If you're an ambitious beginner and if you're an applied worker, you might want to supplement this with more elementary text just to see how the PDEs are actually derived and whether your problem of interest conform to those physical assumptions. Because, I mean, what good is it if an applied mathematician solved the wrong problem? The mathematics might be beautiful, but it's useless in reality. What it could be good from that? A great temptation, a great, so to say, seduction of the beauty of mathematics is that you think math is more real than real life. Right. So this book does not cover the modeling aspect a lot, or numerical simulation. Is very theoretical. Although important, it's important, I think, for user of PDE, it's important to pair that with more domain-specific or more elementary or whatever one with intuitions being exposed. Okay, so this is the one, the natural progression, going from more elementary book by Haberman and more advanced work by Evans. No, it feels like a psychedelic experience. It's okay. I mean, as the more math you learn, the more you realize, the more lenient you become. The more lenient you become when it comes to authors. Okay, you stop demanding everything from them. Okay, and you start appreciating little things they bring up in places that are not usually mentioned. So you start to become more lenient because the more you study, you realize how big the the field is, and the more you study, chances are you're starting to write your own notes and stuff like that. You realize how difficult it is to put together a treatise. So stop looking for the Bible in whatever subject you're trying to study. Okay, especially not for PDEs. You can spend your whole life on PDE. Okay, this is how sublime this field is. This is just there's always so much thing to do, and the thing is, different types of PDE have their own unique techniques, and they don't really translate. Even for the most elementary one, like wave diffusion and Laplace equation, the techniques for handling them are widely different, and they don't really translate well. Imagine more complicated or nonlinear PDEs like Navier-Stokes, like those kind of things. It's very deep. Anyway, so coming back to Teb's comment. Teb's comment is actually what I'm about to mention. There are 3 Russian texts I was about to recommend. Actually, here, why don't we just start with a free resource? Is APM 364 textbook offered at University of Toronto. This one. So this is a textbook written by Professor Victor Ivry. Okay, so I'll come back to the comment on dynamical system, but right now we're dealing with book recommendation on PD. So this one is completely free. It is actually currently being used for the course APM 346 at the University of Toronto. I'll put this in chat so everyone can check this out. This is the book from U of T. U of Toronto, okay? Toronto. So it covers all the fundamental stuff, including more advanced topic. So you can see 1D waves, Kidd equation in 1D, separation of variables, Fourier series, and these techniques were later revisited. Okay, so separation of variable, for example, has its more advanced chapters. Okay. Anyway, and then you have I think mostly we will follow this simply because this is available to everyone and it's completely free. Okay, but for some specific topics, like actually the one we will have this week on Saturday, the one that we do there will actually not following this book. Instead, I'll use my own notes. Okay, but overall, this book is a great book. It also introduced more advanced topic like variational method. Variational method, for example, is important for finite element method. Okay, to apply a finite element method, you first need a variational formulation, and this is connected, of course, to calculus of variation. Not all elementary books mention that. For example, the book by Haberman, I don't think it has it. Okay, but I might be wrong. Okay. Distribution of weak solution. Once again, this is already getting into the more advanced field, not field, but advanced stage of study in the PDE. Actually, we'll see why we need weak solution on Saturday. Just for first order system, you will already see why the classical solution may break down, and you still want some way to interpret the PDE and its solution. Okay, and even has a chapter on nonlinear equations about Navier-Stokes. So as an introductory text, this is great. This is awesome. And As you can probably tell, this is from the Russian tradition. So Professor Victor Ivry is a Russian mathematician, originated from the Soviet Union, and he was a student of, guess whom? Professor Victor Ivry. He's a Canadian mathematician, even though he was educated in the Soviet Union. He was a student of Sergei Sobolev, of no other than Sergei Sobolev himself. So, and actually, I believe he graduated from the Mikhmat at Moscow State University, but he was actually graduated from Novosibirsk, which is also a very strong institution, because during the Soviet time, under the leadership of Nikita Khrushchev, Siberia, in particular Novosibirsk and its surrounding region, was dedicated to like top research in the Soviet Union, and it was like a dedicated city, like I think it's called Science City, or it's called Academy City, right? It's called the Akademgorodok in Russian. So a lot of Soviet mathematicians were trained there and they worked there. So he did mathematical physics, well, a lot of PDE stuff, obviously, and this is his contribution. You can read it on Victor Ivry's Wikipedia page, and I'm just going to put it in chat. So, and he also has other textbooks. Okay, he also has textbooks on ordinary differential equation, complex variable, and also this one. If you guys are interested in this one, perhaps we will showcase this another time. It's on asymptotics and perturbation methods. This is such a cool area, and I think it's such a cool area that still to this day it's not fully rigorized. There are certain techniques that works, quote unquote works, in practice, but lacks mathematical rigorous justification. But it's so cool. But once again, I mean, I don't know if I will do this because it requires a lot of prerequisites. It calls for PDE and complex variable, so we'll see about that. Perhaps some more elementary topics like how do you define an asymptotic series and how it's different from, say, power series. And there's the online version, so there you go. Go click it. Yeah, it's just awesome. There's so many just free stuff available at your fingertip. So there's that. Victor Ivry's textbook on PDE, Introduction to PDE. This is meant to be a first introduction, okay? The PDE textbook is meant to be a first introduction. The topics are largely standard, with some chapters on more advanced material, say in Evans. Okay, and going back to Teb's original comment, there's this book by Tikhonov and Samarsky, Equations of Mathematical Physics, called Equations of Mathematical Physics by Tikhonov. It is translated, yes, it has a Dover edition. So it is very, affordable. So go check this out. Well, we mentioned Tikhonov in the beginning of the stream, right? So because today we only started to read Markushevich's text. Tikhonov and his student Sveshnikov also wrote a book on complex variables, which in my opinion is also a great representative of Russian, not contribution, but style of exposition of complex variable theory. So Markushevich's text focuses on the fundamentals, whereas Tikhonov and Sveshnikov's covers more applications in mathematical physics. But here, this is a dedicated text on PDE. You see, it's only $49 Canadian dollars, so it's pretty cheap for the volume of the book. And yeah, what can I say? It's just awesome. Perhaps I can find a review for that, for that book. Yeah, so we've seen who Tikhonov was, just tremendously productive individual, worked in both pure and applied mathematics, the founder of the modern inverse theory. What else can I say? Used in data science nowadays. known as Tikhonov regularization, and also Samarsky. So Samarsky was a Russian numerical analyst, math. So yeah, Alexander Samarsky. So he was applied mathematician, worked in specializing in mathematical physics, numerical analysis, in particular numerical analysis. I think he was, you can consider him as the representative figure in the Russian school of numerical analysis. So yeah, so he and Tikhonov together wrote this book. Even though the material itself is largely elementary, the depth of exposition is insane. The depth of exposition exceeded well beyond, say, Haberman's text. I mean, I'm not trying to poo-poo on Haberman. Okay, the thing is, there are advantages and disadvantages. So, for example, Haberman's text, as mentioned, prioritize the width, the breadth. For example, there are more techniques being covered in Haberman's text, but as far as the depth is concerned, even though this book is very thick, Equation of Mathematical Physics, this book is very thick. It's like over 700 pages. The equation, the type of equation it covers is not as great. But it does so with such depth. I think it totally makes up for it. So here, can I find a review of that? Can I find perhaps Samarsky? Yeah, I think there was a MacTutor page of history of, yeah, I think there's a review of his work there. Unfortunately, not all of his books were translated. Some of them are still in Russian. We have just in Russian only, Samarsky math. So I was trying to find a book review for that. Yeah. So these are his publications. The theory of difference scheme. This is a foundational work in the in numerical PDE. Okay, this is the finite difference method. This is translated. And yeah, equation of mathematical physics. This one is translated, as I just mentioned. Oh, actually, there's a companion book. Because remember how I mentioned from the beginning, the Russians like to put the textbook and the problem book separate. There are multiple famous examples of that. Okay, there is this, actually, perhaps the most famous of them is Demidovich. It's a collection of calculus book. Okay, it's a collection of calculus problems. It's just with some examples, and most of them is just pure problem, and it's awesome. It's a dedicated problem book. So I guess the Russians did it because the Russian textbooks tend to be pretty thick. If you add all the problems there, then the volume becomes unmanageable. So they have their way of doing things. However, it does mean that to translate stuff, you have to translate both, right? Otherwise, you end up with a book with only exposition and one only with problem. So fortunately, the companion book of Equation of Mathematical Physics has its problem books also translated. So this one is a companion. It's called Collection of Book Problems in Mathematical Physics, also by Dober. And this one pairs with the Equation of Mathematical Physics extremely well. And they are also very, so to say, very physicsy, if you can call it that way. That being said, the proofs are rigorous. So old but gold. And another one. So this is once again written from a mathematical physicist point of view. But if you want a more mathematics for its own sake style exposition of PDE, but with a Russian flavor, go check out Sobolev. So Sobolev's text called Partial Differential Equation of Mathematical Physics. So the names are all pretty similar, you see. Sobolev, Partial Differential Equation of Mathematical Physics, also has a Dover edition. Now, this one is slightly thinner, but and it's also pretty elementary, okay? Do not expect to see actual Sobolev spaces in this book. Okay, this one is elementary. This is not research by Sobolev. Still reading from time to time. Demidovich is a very good book. It's also translated from Russian. Yes. Actually, you know what, guys? Demidovich was the standard of in China. Demidovich was, because it was so old, and back then China was influenced by Soviet institutions. Many of the traditional workbooks were translated from Russian, including textbooks as well. So Demidovich was considered the standard for Chinese students to prepare for their graduate entrance exam, like GRE. If you want to do if you want to do a grad school in China, you have to take the exam, and it's like a standardized exam. And to prepare for the mathematical portion, people it's usually the standard that that students use the Demidovich, and their expanded version, solution, full solution manual were published in Chinese to accompany the problems from Demidovich. But yeah, this one by Sobolev is arguably more rigorous mathematically. And actually in the text it contains a mini course on Lebesgue integration, the measure theory. So yeah, you do need measure theory to study PDEs rigorously. Yes, you do. Actually, guess what? In Professor Ivry's text, Victor Ivry's text here, it is stated. Oh, what's going on? Hopefully the link still works. Preliminary preface. Yeah. Hang on, the next one. What? I'm pretty sure this is an anomaly. There's a PDF format too, so go check that out if the server went down. There's a PDF format, not PDE format, PDF format of the PDE book. Here it says we will not be rigorous in the first introduction, because to prove theorem rigorously in PDE, you need a lot of background in analysis. It says, in this class there will be very few theorems, and the proofs will not be very rigorous. Reason is very simple. Look at ODE class. There were just two existence and uniqueness theorem for the Cauchy problem that require arguments basically from real analysis. So in PDE, a lot of the arguments were based on measure theory and functional analysis. So he says basically one needs to study advanced or very advanced real analysis before taking PDE class, but this is not feasible even for mathematical specialists. So the most important part of modern real analysis or functional analysis grew up from the need of PDEs and mathematical physics, and lesser degree applied mathematics. So yeah, for example, Sobolev spaces. Sobolev spaces is now just a branch of functional analysis on its own, but it arises from concrete engineering problems. So yeah, you need very advanced real analysis to do PDEs rigorously. Yeah, so you can see here PDE by Sobolev. It contains advanced materials like measure integration. It contains a mini course, as I said, on Lebesgue integration, and also integral equation technique. I don't think actually here in the text, based on my experience, the AI is not completely correct here, because the book is elementary. The book is, covers elementary topic. It is not research done by Sobolev. Okay, it's not research done by Sobolev, although some approaches might be novel, but the material largely is standard. Okay, and if you want to know more about Sobolev spaces, go check out Evans instead. Okay. So wow, I just gave how many? 5 books in total. I usually don't do that because I figure that will cause selection paralysis. But I think because of the way Russians do things, the problems and the books are separated. Not always nowadays, but tends to be more common than usual back in the Soviet time. So I consider these two to be the same book. Not the same, but one book. Equation of Mathematical Physics by Tikhonov and Samarsky, as well as this collection of problems in mathematical physics. So let me know if you guys want to see, say, we want to do a PDE Russian style. I mean, this stream is complex analysis Russian style. So if you guys want to see that. Abbott is definitely not enough, unfortunately. So understand basic proof in PDE, Abbott is not enough. Abbott is very, how should I say, just, Abbott is, how should I put this? Abbott is like, is the ABC of analysis. Okay, but still, is it important, but not enough for PDE, okay? For example, let's say here, what we're doing in, what are we doing, say, in Avery's text? What are we doing here? What are the texts? What are the techniques? Separation of variable Fourier series. To do this, I mean, Fourier series, well, you can argue that studying Abbott gives you enough background to study certain aspect of Fourier series. Okay, so Fourier series is a subject that can be approached at many different levels. Or for just Fourier analysis in general can be approached from many different levels. Well, you can't approach it from a discrete level. You just need linear algebra. If you only have linear algebra, then you can already do some Fourier analysis. If you have some real analysis, say at the level of Abbott, you can also do Fourier series to some degree. Okay? But to fully appreciate its power, you need functional analysis, distribution theory, and measure theory, which is a lot. So I'm not saying, oh, it's Abbott or nothing, okay, or real analysis or nothing. These things are, like most areas of mathematics, can be approached at different level, okay? It's just because here, the book is not rigorous, the author tells you that, it doesn't say it's useless, right? You can still work with, you don't always need the most general case. And to do proofs in PD, you definitely need a real analysis, let's say, at the level of Folland. So there's that. It's sad. I mean, it's sad, but at the same time, it's also inspiring, isn't it? I mean, it's discouraging, but it also at the same time is inspiring. There's always math to do. There's no such thing as running out of math to study. I mean, nowadays, because of the AI, a lot of people worry about, oh, there's going to be AI taking over everything. We have nothing else to do. Of course, it's a different subject, but I guarantee you there's always roles for humans to do in mathematics. To be honest, we took PD on the 5th semester of bachelor degree after 1 year of ODE. And yeah, you typically need, I would say, a solid background in ODE and as well as multivariable calculus to do PD even at a non-rigorous level. So yeah, I mean, I'm going to assume, I would say, multivariable calculus, but perhaps not extensive background in ODE. Okay, I'll actually show how the ODEs are solved, but you need to know, let's say, there is this notion called ODE before you approach the PDE, the subject of PDE, right? I mean, to be honest, in my opinion, the subject of ODE should be integrated with regular calculus. It's just how history was done, right? So calculus was largely invented to solve differential equations. Various integration techniques and all kind of stuff. Okay, we aren't just interested in like calculating volumes and all the stuff, because that's important. But the thing is, integration techniques were largely invented to solve ODE. So why don't we just incorporate ODE as part of the standard calculus text? It just always baffles me. Okay, you can have more advanced ODE, but definitely the easy part, or at least the more just, it helps with modeling, because ODE is a great topic for mathematical modeling, and it's a great proving ground for various integration techniques. So why not we add that? And actually, Stewart does have one chapter on it. I just don't know how many standard calculus courses take that seriously. But here, I was saying Fourier series, to do it rigorously, you need measure theory. Fourier transform, well, you need measure theory and distribution. Variational method, well, functional analysis, yeah, distribution here is in the name. So you need a lot of advanced real analysis to really do these things rigorously. Okay, but fear not, it really depends on your objective, say. It really depends on if, let's say, your goal is to understand financial mathematics, if you want to do physics simulation, and if you're more interested in the numerical side of this the story, not all of them is needed immediately. Okay, of course these are all connected, but there's still priorities for one person to know. Okay, and the topic for this Saturday's stream would be first order PDE, and in particular the method of characteristics and its applications. So we'll see some concrete examples how PDEs are derived, how do you solve them, what's the interpretation, and why do classical solution breaks down, that kind of stuff. I was initially going to use chapter 2 of Ivry, but I decided to use my own notes instead. Okay, but still, go check out his work. Even though the material is standard, there's still idiosyncrasies when it comes to exposition. So very, very, very nice book. Just very, and also completed for free. There are tons of exercises. My goodness. Yeah, there's tons of exercises. So you should, even though this is one problem, there's a lot of. It's just the same problem with different numbers. Well, if you change the type of matrix, actually, if you change the matrix, sometimes the question changes qualitatively too, depending on, well, the situation with eigenvectors and stuff. Okay, we're getting too technical here, but there's a lot of problems to practice here. There's a lot of practice problem in this online book by Ivry. Go ahead and check it out, which is awesome. And I think now we are already well over 4 hours, so I'm gonna call it a day. Thank you very much, everyone, for joining the stream. So the plan for tomorrow would be in the morning I'll do a Russian practice, 2-hour Russian practice, and in the afternoon I'll do some tensor. No stream tomorrow evening, unfortunately. Okay, and next week, because I'll be back to work, so streaming schedule would be not as intense as in this week. So, but I'll still try to go online and just chat with you guys. And actually, of course, above all else, do actual math. All right. Thank you guys very much for watching, and I'll see you guys next time.